Thank you everybody for being here, second day. So I'm going to give a really short presentation about introduction to architecture, mainly, of course, on our GPU. So here we have a really nice white paper that you can read a lot of information. Now, on our AMD InstinctTM 250X is 58 billion transistors in 6 nanometers. We have 220 compute units, 880 second generation matrix cores, and we have 120 gigabyte memory, HBM2E with peak performance 3.2 terabyte per second. As you know, this GPU, it is and will be in a Lumi, Dattel, Cines, and Frontier. And if we look at the picture, then we can see basically two dual graphics compute die. So that's why we said when I was saying, when you say select from SLARM GPU 1, you select one of these two. So physically, it's one GPU, all of this, but has dual graphics compute die, okay? And as you can see, you have here 8 stacks of HBM2E, okay? And then you can see that you reserve this path of CPU1, so you work on this specific one, for example. And it's much faster than MI100. So if you have somewhere access to MI100 and something is not performing well, then there's something to dig to find out what's wrong. And if I go inside, I go to GCD. So this is one of the, so if I go inside, let's say here, you go here, okay? So we said now per GCD, we have 110 compute units, and we have 4 matrix cores per compute unit. We have 8 Infinity Fabric links per die, okay? It's on the edge, on top and down, okay? And you can see some memory controllers on the sides. You can see the L2 cache. Matrix cores are enhanced for HPC, like do 64-bit operations, and you have a special FP32 operations for double throughput. It's called the packed FP32. We have also dubbed the BF16 for some other workloads, increase L2 cache, read bandwidth, and the 4 here, the Infinity Fabric technology to interconnect. They're connected to the other GCD on the GPU, and the others can be used also to connect to the other GPUs outside from this specific GPU. And we have 8 shader engines that I will show you better in another shape. So you can see 8 columns that has the other compute units, and the new matrix multiplication instructions for FP64 precision is 2 times higher flops per clock per compute unit rate than general purpose FP64 operations. And so they're really quite strong. And we have double FP64 instruction execution rate compared to MI100. So there were plenty of improvements. Now, here you see the first CD connected to the second one. So here we're inside, here you see the HBM. So it's like a zoom in the first picture. And you can see here the links, okay? So basically, here there are 8 links of 16 lanes bidirectional. So basically, it's 4 lanes of these running at 24 Gbps, but we have so many here that finally is 400 gigabytes per second bidirectional, which means 200 this direction and 200 the opposite direction. Okay, so basically, and as I said before, GCD has 8 times 16 links, and 4 is for internal. Internal is here, and the other is to connect to the other GPUs and also the interconnection, etc. Now, here's a comparison with the MI100. We do that because maybe you had access before to MI100. Before, we didn't have a metric scores with FP64 support for MI100. Okay, here we have, and it has 256 operations per clock per compute unit. So for MI200 series, our clock rate for FP64 is 128 flops per compute unit per clock. So the metric scores are also double than the classic FP64 of the MI200 series, okay? And here, we keep the same. So if you see the same, so if someone runs just FP64, just FP32, the performance will be similar, except if you use the packed FP32 that I will mention later. And we increase also the BF16 and the INT8, okay? So there's some performance improvements compared to MI100. And of course, I will mention, I mean, it should be now probably. So to use this metric scores for matrix multiplication stuff, etc. My first recommendation is use the libraries, right? I mean, nobody writes better code than the people who do the maths behind the libraries and add performance everything. So the ROC Plus has already integrated the metric scores and it will use them automatically, okay? And that's really, really great. You can use intrinsics or rely on assembly. Of course, if you do this, this means that you really know what you're doing and you are expert, etc. So it's not something like to do for fun, I would say. So use the libraries, and other libraries will use the metric scores. Not currently supported. I hope it's still the same. Libraries of device functions utilizing the metrics operations that can be called from kernels, not supported. And abstraction frameworks like Cocos, Rasa, Oka, this would have to use one of the other mechanisms internally, don't support the metric scores. Of course, some things can be developed really fast, and you always have to watch if something changes on this aspect. In general, though, the second generation of metric scores is a really big improvement because it can be used now on HPC, except the AI, okay? And data types and applications newly support metrics FP64 and packed FP32 math, providing higher throughput. And as you can see here, so what you see here's an example for the mini hack. This is an astrophysics or cosmological code. FP64 path used to execute 2-component vector instructions on FP32. And now the packed FP32 doubles the throughput per clock per compute unit. So what happens here is that we're achieving in the base around 22 teraflops, while with the packed is 58. 22, 58 is above double, because with the flow 2, which is the packed FP32, it's not just going to packed 32 running double the throughput, but they optimize data structures and leverage better the LDS memory also. So some new PK instructions about matrix multiplications are supported and improve the performance significantly. And the hack, the code, hit it 43 teraflops in some cases, and is quite strong, as you see. So as you initially, you can say why to do FP32 if performance is the same. The answer is that with packed FP32, the performance is not the same at all. And also, if you this code, you take it and you try to run it on another vendor like NVIDIA, will run as FP32, and it will not, I mean, it will not crash, it will just run. I mean, because I tried some benchmarks. Also, my colleague Noah will present later. It's the person of contact for this this aspect, so you can ask questions also. And it's really something that we are proud for. Now, if I can compare between MI100 and MI250, again, because maybe some people have experience on MI100, we have one graphic compute die. Here I have 2 graphic compute dies, okay? So in order to utilize both GCDs, okay, you need to utilize to reserve 2 GPUs. One GPU, I mean, if you reserve one GPU, cannot utilize the two GCDs. Now, the GPU term is in LARM, right? One GPU has two GCDs. Now, before we had 32 GB memory, now we have 64 GB of HB2E memory per GCD. Totally 128. But if you reserve one GPU, you have 64 GB of memory, not 128. You need to reserve both of them. Before it was 11.45 teraflops peak performance. Now it's 26.5 teraflops peak performance per GCD. Before the memory bandwidth was peak 1.2, now it's 1.6 per GCD again. Before we had 120 compute units per GPU, now have 110 per GCD, totally 220. That's why we were saying before that in OpenIP, how to tune and have a multiple of 110. If you use M-100, maybe you have to have a multiple of 120, number of teams, and all of this information. And before, the connection is attached on the CPU, while now it's attached on the GPU. So it's really benefit for you to use API with buffers on the GPU, right? And both GCDs are interconnected, as I said, with 200 GB per second per direction. 128 single precision FMA operations per cycle, second generation matrix cores, and memory coherency. Now with memory coherency that I think you presented later in the presentation, you can have access on the memory system from the GPU, right? It's not fast, but you can do it for memory coherency purposes. And you have here also a nice white paper. Now, what I want to show you here is this is a image from Oak Ridge's website, but I have edited also a bit. Here is the CPU, okay? You see the 4 numbers of the CPU. Now, the trend basically is a 64-core AMD optimized 3rd generation EPYC CPU, core chiplet die connected to GCD via Infinity Fabric CPU. Now, you can see the parentheses because it's about the multi-threading, right? That's where you see multiple number of, so 64 cores with multi-threading is 128. And what I want to show you here, that my colleague Gina will talk later about Affinity, is about how they connect to GCDs, okay? So the links here you can see is 36 GB per second per direction, okay? And what I would say, if you use a GCD5 and you have your process here in NUMA 2, you have to pay an overhead to go to access to transfer data. So that's why we'll talk about Affinity later, how to map your processes. What I want to show you here is that between the GCDs, the ones that are in the same GPU, they have the 200 GB per second per direction, okay, the red one. But the neighbors, I mean whatever neighbors, GCD5 sends has this one 50 GB per second to GCD7 and 50 to GCD1. But the GCD4 to 2 has 50 plus 50, 100 GB per second per direction, plus 50 GB per second to GCD6. So, I mean, there is some difference between which GCDs you're communicating, what's the peak bandwidth, okay? It can be a bit complicated, but okay, I mean, you will get use of it. And here, I want to show you some simple things, just to, sorry, you see here the shader edges, the eight shader edges, right? I will go back, a bit back, sorry, to show you the eight shader edges, okay? The columns here. So just here we we make a design much more simple. So there are 8 shader edges that have decided the compute units. This is the one GCD, right? One GCD only. So the request comes and go inside. But how they go inside? Here you can see that there's a command queue, and you can see the queues is reside and user visible in the DRAM, and the request comes, split it in the specific task according to how the HSA decides, and the workload manager decides which shader engines will take the workload and which compute units. Here you see the compute units, right? There are plenty of compute units per workload manager. We have totally, as I said, 110 per GCD. Okay, so this is how basically it's split. So if you don't have enough workload and you fill in 1, 2 shader engines, then don't expect that the performance will be significantly big for your application. That's why you always need to know the architecture and how many compute units I have and how much data I need to have to stress the GPU. And that's why sometimes if you compare a CUDA code from another GPU to this one, maybe it doesn't have enough workload. This happened to me many times. I need to increase the problem size to stress our GPUs. So overall, this is what I want to tell you. It was really a short presentation, but I want to show you how it is, and of course, answer any questions orally, or maybe I will check the HackMD. I see it's almost time for our next presentation.
Okay. Hi everyone, my name is Madia, and I'm going to talk about GPU-aware MPI communication with ROCm. First, I would like to thank my colleagues, Bill, Bob, Leopold, and Justin on helping and contributing to gather this material. So first, I will provide an introduction, and I'm going to run some examples of using GPU-aware MPI on cloud and Lumi. We have some examples with point-to-point communication and also collective communication. And then I'm going to discuss what are the communication options that we have with MI250 and how are the GPU placements on Lumi. And we are going to use OSU micro benchmark to measure communication bandwidth and latency for point-to-point and collective communication. So as you know, MPI is a standard for communication in high-performance computing. Processes in MPI, they have their own private address space, and we can run MPI programs on systems with distributed memory space. MPI standards defines message passing APIs for handling different kinds of communications, including point-to-point and collective communication. But what is a GPU-aware MPI? So in the past, most of the MPI implementations, they only supported passing host buffers to the MPI calls. But with GPU-aware MPI implementation, we have this opportunity to pass GPU buffers to MPI calls. Without GPU-aware MPI, we cannot pass GPU buffers to MPI calls. So we have to copy the data from the GPU buffers to the host buffer and then pass the host buffer to MPI calls. And this has some overhead. Currently, many MPI implementations have support for GPU-aware MPI, including CrayMPitch and OpenMPI. What is GPU Direct RDMA? GPU Direct RDMA is a technology that provides the opportunity for network adapters to directly read data from GPU or write data to GPU, and this way we can completely bypass the host. People sometimes confuse GPU Direct with GPU Aware. So GPU Aware MPI refers to support passing GPU buffers to MPI calls, and it's usually used in the context of MPI implementations. But GPU Direct is referring to the lower levels of software stack, and it's a technology that enables direct access to GPU memory. And a GPU-aware MPI implementation may or may not use GPU Direct RDMA for communication between the GPUs. So in this slide, I'm showing an example of a GPU-aware point-to-point communication. So first, we are allocating the buffers. We are allocating the buffer on the host with malloc and on the device with heap malloc. And in this example, rank 0 is going to send data to rank 1. So we initialize the buffers. On rank 0, we have the send buffer, and we are initializing it to some integer values. And on the receiver side, we are initializing the buffer to -1. And then in our code, we can have like different kernels to change the buffers and so on. And then at some point, we want to do the communication. So on rank 0, which is the sender, we are calling MPI send. So this is like calling a conventional MPI calls, but instead of passing the host buffer here, we are passing the device buffer to MPI send. And on the receiver side, we are doing the same thing. It's like similar, like the conventional MPI receive call, but we are passing the device buffer to the call. And then after that, we are validating the results and we free the memory. For freeing the host buffer, we are using free. And for the device buffer, we are using heap free. In this slide, I'm showing an example of running GPU over a collective communication. So first, I'm showing how we can set the device. So in this example, we want rank 0 to be executed on device 0 and rank 1 to be executed on device 1. So for that, we are calling heap set device, and we have rank as the input of this function. So this way we can have each rank assigned to one GPU. And I assume that in the node we have 8 GPUs in total. And then we just want to make sure that each rank has the right device number. So we are calling heap get device. So heap get device has the device ID, the pointer to the device ID, and it returns the device ID for us. And then we are printing each rank with its device ID. Then we are going to allocate the buffers. So first we allocate the buffer on the host with malloc, and then we allocate the send and receive buffers with heap malloc on the device. And then we initialize the send and receive buffers. Again, we can launch some kernels in our code, and at some point we want to do the communication. So in this example, we are showing MPI reduce example. And as you can see, we are passing the device buffer to MPI reduce, and the rest is the same as like a conventional MPI reduce. And then we validate the results and we free the memory on the device with heap free. So what if we don't have GPU over MPI? If the MPI implementation that we have doesn't have support for GPU over communication, then we have to pass the host buffer. And then we need to have some extra mem copies to copy the device buffer to the host buffer. So for example, in our point-to-point communication, if we don't have GPU over MPI, then we need to copy the device buffer to the host buffer on the sender side and pass host buffer to MPI send. On the other hand, on the receiver side, we pass host buffer to MPI receive, and then because we want the data to be present on GPU, then we have to copy host buffer to the device buffer. So if we don't have GPU over MPI, we have an extra copying between the device and host. So in this slide, I'm showing the instruction to build and run a GPU over MPI example on Cloud and Lumi. So on Cloud, we have OpenMPI module available. So you need to load OpenMPI module, and also you need to load ROCm. And then we need to set the wrapper for OpenMPI. We do that by exporting OMPI CXX to EuroCC. And then we can compile the code with MPI CXX, and we can run the code with MPI run. On Lumi, we have CRAY-MPICH available as MPI implementation. So we need to load the module with CRAY-MPICH and ROCm. And so for compiling with CRAY-MPICH, we have two options. We can compile with Cray compiler wrappers and link ROCm. So here in the first example, you can see I'm compiling with CC, which is Cray compiler wrapper, and then I'm adding the include directory path with -i, and also I'm linking ROCm path. And the other option that we have is to compile with EuroCC and link CRAY-MPICH. So here I'm compiling with EuroCC, and I'm including the include directory of CRAY-MPICH, and also I'm linking CRAY-MPICH. We also, for supporting GPU over communication, we also need to link GTL from CRAY-MPICH. And then for adding support for GPU over communication, we need to set this environment variable, MPICH GPU support enabled to 1, and then we can run the code using srun. So right now I'm going to show you some examples of measuring bandwidth on LUMI. For that, I'm using OSU micro benchmark. OSU micro benchmark is a MPI benchmark that measures the performance for different MPI operations, including point-to-point communications, collective communication, and also it has a test for host-based or device-based communications. So you can get the OSU micro benchmark code from OSU micro benchmark website, and then you can extract a file for configuring it. So you can set the prefix, where do you want it to be installed. And so I'm running it on LUMI with Cray MPH. So I'm setting CC and CXX to point to the Cray compiler wrappers. And for enabling testing with for device communication, we need to add enable ROCm, and also we need to add the path for ROCm. And for enabling, again, GPU-aware communication, we also need to link it with GTL in Cray and pitch. And then we can compile it with make and make install. So what are the options that we have for GPU to GPU communications? So we have two options. One of them is using STMA engine, and the other one is using bleed kernels. STMA engine provides the opportunity to overlap communication with computation. But the drawback of using STMA engine is that it can provide a maximum communication bandwidth of 49 gigabytes per second between the GCDs. The other option that we have is using bleed kernels, which we actually launch a kernel to do the communication. The advantage of using bleed kernel is that it can provide higher communication bandwidth. However, we cannot overlap communication with computation. Right now, in the current ROCm version that is available on LUMI, we have ROCm 5.0.2, which has STMA as a default way of communication. Whether you should use STMA engine or bleed kernel, it depends on your application. If your application can benefit from overlapping communication with computation, then it's better to use STMA engine. Otherwise, if you care more about just bandwidth, it's better to use bleed kernels. So in this figure, I'm showing the maximum achievable bandwidth that you can get for communication between the GCDs on LUMI. As you can see, there are like different number of links between different GCDs. For example, for the GCDs that are located on the same GPU, there are 4 links. There are 4 Infinity Fabric links, and the maximum bandwidth that we can get is 145. However, like for communication between GCD 0 and 2, there is 1 link, and we can get around 35 gigabytes per second. So how much bandwidth we can get out of communication, it depends on the number of links that is there between the GCDs, and also the number of hops. Like if GCD 0 wants to communicate with GCD 3, then it should go through 2 hops. So it has some more latency, and which can impact the performance. So here I'm measuring the intra-node GPU to GPU communication bandwidth. It's actually a demo to just show how we can measure the bandwidth. So for running it on LUMI, we need to load ROCm and Cray MPH module, and also we need to set MPH GPU support enable to 1 to enable GPU-aware communication. So in this example, we want to use bleed kernels. So we are setting HSA enable STMA to 0. So I'm using OSU micro benchmark to measure the bandwidth between different GCDs, GCD 0 to 1 to GCD 0 to 7. And to force the communication to happen between GCD 0 and 1, I'm setting keep visible devices to 0 and 1. And then I'm using srun command. I want to run the test on 1 node with 2 processes, and I'm using OSU bandwidth test. With -m, we can say the message size, and with using DD at the end, we are actually forcing the communication to happen between GPUs. So as you can see, for communication between GCD 0 and 1, we can get 142 gigabytes per second. And so if we go back to this figure, you can see that for communication between GCD 0 and 1, we are getting close to what is expected. For communication between GCD 0 and 2, we are getting 38 gigabytes per second, and that's because we are limited by one link between GCD 0 and 2. For communication between GCD 0 and 3, we are getting 36. So you can see the bandwidth that we are getting is slightly lower than what we are getting between GCD 0 and 2. And the reason is that we have 2 hubs for communication between GCD 0 and 3. And we have the same reasoning for the rest of rest of the communication shown here. So this slide shows the communication between GCD 0 and different GCDs, but this time we are using SDMA engine. So we are setting HSA enable SDMA to 1. And as you might remember, I just said that with SDMA engine, we can get the maximum bandwidth of 49 gigabytes per second. So as you can see, we are getting the maximum bandwidth that we are getting is 49 gigabytes per second. Although there are some GCDs that have lower communication bandwidth, and the reason for that is that they are limited by the Infinity Fabric link because there is just one link between GCD 0 and 2. And just to summarize, with SDMA engine, we can achieve up to 49 gigabytes per second. With lead kernel, we can achieve up to 142 gigabytes per second. And the communication bandwidth that we can get between different GCDs depends on whether we use SDMA engine or bleed kernel, the number of links between the GCDs, and the number of hops between the GCDs. And so we are just summarizing the bandwidth numbers that we got. In this slide, I'm showing the internal communication bandwidth. And again, I'm using OSU micro benchmark. So I'm running with srun command. I force it to run on 2 nodes and with 2 processes. And I'm using OSU bandwidth test. And I'm using DD to just tell that I want the communication to happen between the GPUs. And as you can see, we can achieve close to 25 gigabytes per second bandwidth, and so this is the bandwidth that a slingshot network can provide, and this is good to know that we are getting close to what the network can provide. This slide shows the GPU-aware collective communication. So the example on the top shows the run on 2 nodes. So we have -N2, which tells that we want to run this test on 2 nodes. We have 8 ranks in total, and we want 4 ranks per node. And in this example, we are using OSU reduce test. We want to show the numbers for size 4 to 128. And we are passing -D ROCm at the end. With passing -D ROCm at the end for collective communication, we are forcing the communication to happen between the GPUs. So we have 4 ranks on node 0 with this method, and we have 4 ranks on node 1. The other example is showing the communication on 1 node. So we have -N1, and we have 8 ranks in total, and the number of ranks per node is 8. And again, we want the communication to happen between the GPUs, so we are adding -D ROCm at the end. And so this way we have 8 ranks running on 1 node. And as you can see, when we have all the ranks running on 1 node, we can get a lower latency compared to doing the communication between the nodes. So to conclude, we showed that GPU-aware MPI provides the opportunity to pass GPU buffers to MPI calls. Right now, many MPI implementations have support for GPU-aware communication, including OpenMPI and CrayMPI, although we need to sometimes set an environment variable or link GTL, like for example for Cray and Pitch, to enable GPU-aware communication for these implementations. And we use OSU micro benchmark to measure the communication bandwidth and latency between the GPUs, and we measured intranode and internode communication bandwidth. We showed that the communication bandwidth between GCDs depends on whether we use SCMA engine or grid kernels. It depends on the number of links between the GCDs, and also it depends on the number of hops between the GCDs. And we also showed an example of running collective communication, and we measured the performance for when the collective communication is running on one node versus two nodes. And thank you for your attention.
Okay, let's hand over to Bob then.
Okay, so we're going to be talking about the memory model for the AMD node. This gets into some complexity, but it also makes some of the programming easier. So it's a very key development with the AMD GPUs. So this material, Alessandro, Carlo, Michael, and Nick Curtis have all contributed to these materials, and thank them for their contributions. So what are we going to cover here? There's a lot to cover. We're going to first talk about coarse and fine-grained memory. We're going to talk a little bit about atomics because they're closely related to this idea of coarse and fine-grained memory. We'll talk about page migration and how it gets moved from the CPU to the GPU. OpenMP has some support for this, and you have some way to access the same sorts of things from within an OpenMP program. And then we'll talk a little bit about where it's going from there. So what do I mean by a memory model? So with parallel computing, the memory model defines the rules for synchronization of memory and the changes of memory between threads or processors and cache. It's a critical thing for parallel programming, because if you do this incorrectly, you can have race conditions. You can be grabbing old data when it's been updated by somebody else. So let's look at what the model is for this hardware. We'll start with managed memory and page migration. So HMM is heterogeneous memory management, and it's part of the kernel. It helps migrate pages from one device to another. So if you have a pointer on the CPU, you also have a pointer on the GPU, and the memory gets migrated between the two of them. The pointers still exist on the other device. And so there's some considerations. For example, on the CPU, is the memory still swappable? So it's not in pin memory, it's migratable CPU memory. That can still be swapped out. This XNAC is the term that is used to refer to retrying memory accesses. So it's part of the internals of the AMD GPU that grabs the memory when a page fault occurs. So if you're on the GPU, it tries to access a page of memory, it fails, it's then going to go try and grab it from the CPU. There's a couple environment variables which turn this on, and you can have a default but by setting the environment variable HSA XNAC equal 1, you then enable this migration of memory. There's also a compiler flag, and there's 3 settings for the compiler flag. You can have XNAC plus, XNAC minus, and XNAC any. So you can add this keyword to the target offload architecture equals GFX 90A. You can add that keyword to it to get that compilation mode. So it can be pretty complicated because you got controls on the system. During boot, you have environment controls and you have compiler controls. So you can still explicitly move pages from the CPU to the GPU. You can use this prefetch async call, or you can have this automatic page movement of memory from the CPU to the GPU and back. You have to have support in the hardware and in the operating system, and you have to have the proper flags set. Right now, there's a lot of interest in detecting when that page migration occurs. Our tools, we're still working on a mechanism to detect that memory movement. You'll hear a little bit about the tools tomorrow. Hopefully, we will have a presentation on how to detect page migration in the near future. As we've talked in previous presentations, there are different kinds of allocators you can use for allocating memory on the host and on the device. And only 2 of these allow the page migration. So that's the system allocators, such as malloc or HIP-malloc managed. That could change. So you have to check what the current status is with the software. So here we have, we're allocating the memory on the system. So this is on the host with a malloc call. We're going to initialize it on the CPU, and then we're going to call a kernel on the GPU. Now notice we have not moved any memory. We are just calling it on the GPU, and it's going to migrate the memory over to the GPU automatically. So if we do alignment, we can improve the performance, although the first call can be a little bit slower. So if you do not have the environment variable set, no migration will happen. It will stay on the host device. When you set that variable to 1, the migration will happen, but it may vary depending on the alignment. So there's a lot of interaction between the operating system and how this memory gets moved. So HIP-malloc managed is a more reliable allocator for page migration. And so here's the same example with that when we allocate it with HIP-malloc managed. And you can see that the first time is still a little bit slower, but it's a little bit better than the previous ones. And then in this case, when we do it back on the host, you see that the transfer for the first time it's used is a little bit slower. So you can prefetch the memory. It's called async, but right now it's not asynchronous. There's plans to make it asynchronous. You can do it in either direction. So you can force the memory to be moved earlier. That can help with some performance issues. You can also change the attributes of the memory with this memAdvise call. So we can set different, a preferred location. We can set properties to it that change how it behaves. There's still a lot of potential for changes in this call with capabilities as we get more experience with this page migration. So here we're using that memAdvise call to set the coarse grain attribute for the memory. So we can change the kind of memory that we get back from the malloc call. It does operate at page granularity and do keep track of current changes to HIP memAdvise if you're using it. So here in this table, we're showing 4 different memory allocators. So what happens when we use this memory and doesn't migrate? So for in-place memory on the CPU, we're going to have it local for all but the HIP malloc, which will be remote because that's allocating the memory on the device. And the GPU access is going to be the opposite. So do we get automatic migration to the GPU? In this case with HSA XNAC 0, we do not, so none of them migrate. And we have only prefetch async support for the malloc managed. And the granularity that comes back from these is different. So for 2 of them, it's fine grain, and 1 of them, it's coarse grain. Now, we'll be talking a little bit more about this fine and coarse grain memory and why that's important in the following slides. So with HSA XNAC turned on, set equal to 1 in the environment, you'll see all the memory starts to migrate from any of these cases. So HIP malloc and HIP malloc managed, you'll see it's migrating between the CPU and the GPU. It's done automatically. And the memory that gets returned is fine grain. So let's look at some sample code for that we're going to play around with for trying to understand what's happening with the managed memory. So if you take this code, it's from the HIP examples. It's also in the AMD training exercises in managed memory directory. And there's a vector add that we show over here on the right. And it's fairly typical HIP code. You're going to malloc the memory, initialize the memory, malloc it on the device, then copy it from the host to the device and launch the kernel. So that's the original code from the vector add example that we borrowed from the HIP examples. Now we're going to change this code. And if you go in, and we'll do this in the exercises if we have time after Madia's demonstration. But you can also do this on your own and take the example code that we have. And all these changes have been done. So if you go into the managed memory directory, you'll see that there's a vector add 1, a vector add 2, a vector add 3, and all these changes I'm showing you have already been done. You can examine them, or you can try to do them yourself. But the idea here is that we only have one memory now, and conventionally, when you're working with GPUs and CPUs, you have a pointer on the CPU and the GPU, and you have to manage it, or you have to help OpenMP manage it. And so you constantly have to be aware where that memory is and which pointer you're using. And that leads to a whole host of problems. In fact, the leading error in GPU programming is using the wrong pointer when you're trying to do something, supplying a device pointer where it should be a host pointer. Well, this sort of eliminates all of that. And so what we're doing here in the first steps is we're going to change all the host and device strings to just vectors, so that there's only one pointer as far as we're concerned. And so we're going to take out half the allocations. We're not going to need any of the move statements. So if you see over on the right, we've commented out a bunch of things. We have changed the host and device to just a vector. And so it greatly simplifies the code. So that's the plus for all this complexity. And that's a huge plus, because the management of that memory is the most demanding aspect of our writing our application and trying to get it to run on the GPU. So in this example, we remove those duplicate declarations, made them all vector, got rid of the memory movement. And then before we get the result, we're going to add a HIP device synchronized to make sure that all the kernels have completed before trying to retrieve the data. And if we do this with that example from the vector add, from the HIP examples, it's going to fail because there's a memory access fault. And that's expected because we're trying to access that memory. We do not have memory migration enabled. So then the next step is set that flag and the test will pass. It will automatically migrate data. So our second experiment is to comment out the malloc and freeze instead of the HIP malloc. And if we unset the HSA XNAC variable, the test still passes because that memory will migrate. We can change that HIP malloc to HIP malloc managed. I'm sorry, that previous one was allocated on the device, so it already exists on the device. HIP malloc managed, that one will migrate, and so the test will pass if we do the same experiment. So how do you use this capability? Well, unified, or it's sometimes called unified memory or managed memory. So it can be very helpful in initially porting an application, because as you move each loop over to the GPU, you have to move this data movement along as you try to go to the next kernel and get it running on the GPU. So it's a lot of lines of code you're moving around, a lot of potential for mistakes. If you just have you have this automatic movement of the memory, you can focus on the kernels, and that speeds up the porting of each loop, and it can be done much faster. Now, it could be that at the end, you want to add explicit memory management. It gives you more portability, and you might gain some better performance because you're in control of when that happens. So The typical scenario here would be use the managed memory while you're developing the code. And then at the end, and that means you have to work on a system that supports managed memory. But at the end, you could add the explicit memory management and it would be portable to more types of GPUs. The HIP-malloc managed tends to provide the best performance. You do have to worry a little bit about alignment if you're using the malloc call. And if you're using hip host malloc or hip malloc, the memory pages will not migrate, at least currently. So we're still working on performance issues with the page migration. And so that may change with time as the software gets tuned for this capability. So let's go back. I mentioned coarse and fine-grained memory. And so what is that? Coarse grain gives you a different coherency than fine grained. So with coarse grain, at kernel boundaries, everything is synchronized. And so you don't have any coherence issues once you've exited a kernel. Within fine grain, you can get coherency within a kernel. And so the CPU and GPU can synchronize while the kernel is running. Now, this is actually a really important capability that we can use to get better coherence, finer coherency within the system. Since it's so new, it hasn't been totally exploited within the software, but it can help a lot if you try to get coherency, because currently with GPU programming, one work group cannot interact with another work group or with the CPU. So it's giving you a better capability of accessing information while the kernels are running. So there's 4 allocators we're going to talk about here, and they all behave differently. So hip host malloc and hip malloc managed return fine grain memory, and hip malloc returns coarse grain, and malloc and new return fine grain by default. We have different properties being returned from all of these allocators. You can also set it with the hip mem advise call that we talked about earlier. And as this is fairly new, it's still being implemented, and the features are changing with hip mem advise. So what granularity do we get back? Well, we get we can add a flag to the malloc calls that give us different kinds of granularity back. So the default, as we showed before, is if you don't have any flag, but you can set different kinds of flags for this this coherency attribute for the memory. And again, these are still being experimented with, and should provide some special capabilities in different situations. Okay, so within our mem advise, we have some flags also. We can change the type of memory we're getting back. So with this, I've introduced what coarse and fine-grained memory is. How to use this is still a an active development, and we'll have more material on that in the future of how to use this to your advantage. Right now, I'm going to go and talk about atomics and how they interact with this fine and coarse grained memory. So the MI250X has a set of hardware atomics for both integers and floating point. In these examples, we'll use the atomic add. This atomic add can be either a true atomic operation, or it can be a compare and swap operation, depending on different settings. We prefer the hardware accelerated atomics where we can use them. But if you use the hardware accelerated atomics on fine-grained memory, it will fail. And that's because of the synchronization, the coherency that fine-grained memory has. So by default, the compiler will use the compare and swap loops, which is a software implementation of that atomic add. So it's going to loop across that memory location and make sure that nobody else is using it, and then do the add, so that if another thread is accessing it, it will not modify it while that operation is occurring. So those compare and swap loops are slower than atomics. And generally, because it's done in software, atomics are supposed to occur basically in one cycle, or at least conceptually in one cycle, where nobody can interrupt the operation. So there's a flag, and the flag is M unsafe FP atomics. And that's basically saying to use the hardware atomics. It's kind of an odd way to tell you to use the hardware atomics, but it is also warning you that it may be unsafe in some situations. So if you are on coarse grained memory, you are fine using the hardware atomics. And you can also use the unsafe atomic add within your code rather than an atomic add, and it will always do the hardware atomics. So there is also some variation depending on the version of ROCm you're using. And if you're using, since ROCm 5.2.0, which is on most of our systems today, it will enforce those hardware atomics. So this applies only to floating point atomics. The integer atomics will always be done in hardware. So what's the summary here? If we, I hate double negatives, but -M, no unsafe floating point atomics, will do the compare and swap loop. And if you use the unsafe atomic add, it will always get the hardware atomic. If you just use M unsafe FP atomics when it's later than ROCm 5.2, you will get the hardware atomics. Do be cautious when you're using this to make sure that you are getting the correct results. There is a variation in the performance of all of these. I'll show the relative performance of these in one of the following slides. So this shows the performance impact in a application that we were working with. So it had a lot of atomic adds, and if we used coarse grained memory with hardware atomics, I'm marking that as the base level 1. We can get a little bit faster performance with fine grain and hardware atomics, but of course that's going to give us the wrong answer. And so what we would prefer to happen is to have coarse-grained memory with hardware atomics, and that's going to give us the best performance and the correct answer. Compare and swap loops are going to be a little bit slower, and it will vary a lot on your application, what the relative numbers are here, but we can see that it can be a couple of order magnitude slower when you're using a compare and swap loop. Okay, so using that M unsafe floating point atomics flag will turn on those hardware atomics, and then you need to make sure that your memory is coarse-grained. So you'll have to track any memory you're using. This is only important for memory you're doing atomics on. So if you're going to do atomics, make sure that memory is coarse-grained. And check your code to make sure that you're getting the correct answer when you're using atomics, because it can be a little confusing. So let's look at OpenMP and how that works, how these atomics and the shared memory work. So here we're going to use the OpenMP compiler from AMD that is supplied in the ROCm stack. So that's located in the ROCm directory under LLVM bin Clang, and then we set the architecture type, and in the 200 series cases it's GFX 98, and then we're going to set that export HSC XNAC flag, and to track what's happening we're going to use these environment variables to get some debug output. We add that line, the pragma line, to tell it to run on the GPU. Now you notice the lines above, we are initializing the data on the CPU. And so our malloc call is going to be migrated automatically by the system. And you notice that we have the map call. That is going to tell the system that we need to map the memory over to the GPU. And when it does that, it's going to make it coarse-grained. So we don't need to do that map call. It just changes the behavior of the memory. So we take that map out. The migration of the memory will occur, and our malloc, which was fine grain, will then also cause it to be fine grain on the GPU. So if we do supply those maps, then they switch to coarse grain. This is using the unified shared memory, and so it's going to move it over to the GPU. And without that map, it's going to be fine grain. If we put the map in, it's going to be coarse grain. It's also sticky. So if we map it initially over to the GPU with a map call, the subsequent calls will also be coarse grain. And that's repeated here and shown with the subroutine. So the subroutine, it might be in a different compile unit, a different file, and it's telling it to map it, so it's going to be coarse grain because of that map call. And so when we use it later in our main code, it's coarse grain. So here's sort of a summary of the of how that behavior occurs. So we can have when we use the map clause, it's going to cause it to be coarse grain in when we're in unified shared memory. And when we do the these other allocators, we can also control what kind of memory we're getting. So OMP target alloc, we're going to go ahead and allocate it directly on the GPU. So here's another example of this floating point atomics on that kind of memory. So we've talked about when it's coarse and when it's fine. We're adding this OMP atomic hint. And so we're doing basically a reduction here. And by adding this OMP atomic hint and the fast FP atomics attribute to it, we're telling it to go ahead and use fast atomics. And because this memory is fine grain, that's going to fail. So there's two ways to fix that. One is to add this map clause. So we've been talking about how that map clause would switch it to coarse grain. And so that will then cause the atomic to work properly. We can also do a compare and swap by using the AMD safe floating point atomic. So we have a couple of different ways of controlling that. Now, the safe FP atomics will do a compare and swap, so it's going to be a little bit slower. So again, we have this table of how all of these things interact. And yes, it's confusing. But so if we have our compiler flags with the unsafe floating point atomics, that turns on the atomics unless we're using that safe floating point atomic flag. So I do want to conclude with this, that some of these are extensions to the OpenMP standard, at least currently. And so they're specific to the AMD architecture. We may see some changes with that, or we may see changes with the standard to help adapt to this with other GPU hardware. So be thinking about the portability of what you're doing, and not just what works on the AMD hardware. You do want it to be portable across different GPU devices. And much of this is still in development, and so also be aware of any changes in the software stack or the hardware as we go forward, because it may change in the future. And that's all I have.
Am I right that we are going into a exercise now?
Great.
Okay. So we have two exercises here. The first one is testing point-to-point and collective communication, and run some examples. So you can get the node first on the cloud, and on the cloud we have OpenMPI available. So you need to load the module for OpenMPI, and also you need to set the wrapper to use EuroCC. And then you can use these commands to compile and run the code. So we have two examples. One of them is for point-to-point, and the other one is for collective communication. So for the second exercise, we can measure the bandwidth using OSU micro-benchmark. So I'm not sure if you can get 8 GCDs, but if you can get 8 GCDs, then we can measure the bandwidth for different pairs. Again, we need to load OpenMPI and ROCm. And so these two commands here are just to see if OpenMPI has support for GPU-aware communication. So when you use OMPI info, actually I can show you here. So I'm on the node, so I can run OMPI info. And then in the output, I can see the configure command. So here you can see it is configured with UCX. And so we can see, now we can see how the UCX is built. So if I go to this directory and then run UCX info command, UCX info-v, then I'm getting the config command for UCX. And here you can see that it is built with ROCm. So this shows that the MPI implementation here has support for GPU-aware communication. So it's just to check things, but I think like most of the systems that you have access to, they have support for GPU-aware communication. And then you can run the OSU macro benchmark test. You can get the benchmark from this website, and then you can configure it and compile it. After it is compiled, you can measure the bandwidth for different pairs of GCDs. For example, here we can set heap visible devices to 0 and 1 to select GCD 0 and 1. And we want to run the test on one node with 2 ranks, and we want to run OSU bandwidth test in point-to-point communication sections. And here I'm setting the size of the buffer. You can try different message sizes. I set a buffer size to 16 megabytes to make sure that we can achieve the maximum bandwidth. And we set DD to make sure that the communication is going through the devices. So you can set heap visible devices to different pairs of GCDs and see like how the bandwidth changed. And also we can try different communication options with HSA enable SDMA to measure the communication bandwidth when we use SDMA engine versus when we use bleed kernels. So these are the two exercises for the GPU-aware communication. Yeah, I think that's all from my side.
Okay, so we went through the MPI examples. Now we're going to look at the managed memory. So that AMD file, tar file that we used in the prior one, go ahead and unpack the tar file if you haven't done that already, and then go to the managed memory directory. We're going to need ROCm. And then if you just make that first example and run it, that checks and makes sure that you have the original code running. If you want to do the changes yourself, the instructions are down here. Globally change all the host and device strings to vector, and that'll make it into the managed memory version. You'll move the allocations above the initialization loop, comment out the data copies, and add the synchronize command. That is in the second example if you just want to compile it and try it. And you'll notice that if you don't have the page migration turned on, it will fail. If you turn on HSA XNAC equal 1, then it should pass. And you can experiment with the malloc and freeze and using different variants of the malloc command, hit malloc, hit managed malloc, etc. Those are pretty quick tests to run. You can probably go through those and see what the differences are between the files and see what difference in behavior you get. There's 4 examples, I think, there that try different variants of this managed memory. Then, if you want to try the OpenMP atomics, so I'm skipping the HIP atomic example, and due to time, we'll just look at the OpenMP atomics. So to set that one up, it's in the atomics_OpenMP directory. Again, you load ROCm, but you also need the AOMP module. And you set your CC flag, compile flag to the Clang compiler. And in this case, we've added that pragma statement with the map, and the map clause will cause the data to be copied from host to device. We're not using unified shared memory here. The OpenMP runtime will copy that data over for you. So we run that, and that should pass because that's standard OpenMP. If we remove that map clause and add the require unified shared memory, if we don't have memory migration turned on, it's going to fail. If we have it turned on, it should move it. So we turn on that HSA XNAC, and that causes it to run properly. So you can try the different variants of to make it coarse grain by adding the map clause. But let's move on down to the ROCm 8, which has the atomic reduction. And there we have this atomic hint, and the test should fail because the memory is fine grain. We add the map clause, and then it will pass because now the memory is coarse grain. We can also change that atomic pragma to the safe version, and that will also cause that to run properly. And today we have the reservation till 5:30. So if you don't get to some of these exercises and want to keep them on hand for at the end of the day and go back to them, there will be additional time with the reservation till 5:30.
Hopefully that comes through. All right, I guess we'll get started. Okay, so I get the pleasure to talk about something that I really enjoy. Hopefully when we get to the end of this presentation, you'll agree with me. But I'm going to be talking specifically about the hierarchical roofline methodology and how we do it on AMD's Instinct MI200 GPUs. And this is work done largely by my colleague Xiaomin Liu, who developed this tool that I'm going to be talking about. But I'm going to get to present some of this material to you. Okay. So it's kind of a packed agenda, a lot to go over. First, I'm just going to go over a introductory to the Roofline, sort of a Roofline 101 course, get everyone on the same page. And then I'm going to run through how we can generate this empirical Roofline on AMD hardware specifically. I'm going to go over this new tool, OmniPerf, which is publicly available, and show you how we can collect the performance and visualize it in this framework. And then finally, we're going to go through some examples. Start off with some simple synthetic workloads like add, multiply, FMA, and then step up to a proxy app, an n-body proxy app, and then finish with some HPC application results. Now for some motivation. I think this audience is pretty up to date on sort of the global HPC architecture space. But just to refresh, obviously we have Lumi, and that's going to have our AMD Instinct MI250X GPUs, our accelerators. But if we allow ourselves to look into the future, we're going to have new architecture, coming out with Frontier, a new AMD accelerator. And even beyond that, we expect more architectures, right? So the takeaway I want to focus on here isn't sort of this marketing, the metrics for each architecture. It's that, from those users that are the most important ones for these systems, that's the the domain scientists, the application developers, performance engineers, those that are trying to extract more science out of this new hardware. You keep getting presented with this new hardware, and so it's a challenge to understand, am I getting the most performance out of this new hardware? The first step is to get your application just running on this architecture. And when you get there, great job. But is that it? Are we done? Is there more, overhead, some more room for us to improve our performance on this architecture? And those are sort of the questions that Roofline comes into and helps us answer. It gives us some sort of bounds on expectations for this hardware, for our application, and gives us a hardware agnostic, even application agnostic metric for measuring utilization of this hardware. So with that background, that introduction, now we can move on to a quick refresher. I think this has been covered a bit already, but the AMD MI200 architecture, sort of in one slide. And here we have our very artistic rendering of a GPU, our gray box. And within our MI200 GPU, we will have two graphics compute dies, GCDs, that's these two blue boxes, assuming we have an MI250, MI250X. And then within each GCD, we have multiple compute units. And within a compute unit, we have our local data share, our shared memory. We have our scalar unit and registers, our vector units and registers, and L1 data cache. All of our compute units will meet up in the L2 cache. Then we have our data fabric for accessing our pure GCDs, other GPUs, CPU. And then through our memory controller, we finally reach out to our global memory, or our HBM memory. So that's just something to keep in mind when we step through some of these hierarchical roofline plots. When we look at some of the data points and arithmetic intensities, keep in mind this specific hardware. And here with this slide, I'm not sure if everyone's familiar with Quentin Tarantino, but he's a movie director who likes to show the ending to the movie, really get you excited, and then bring you back to the beginning and show you where he came from. So this is what I'm doing here. I'm showing you some results. And if you're familiar with the roofline plot, then you should be able to take away, within 10 seconds, the main takeaways from this this plot, and you can keep moving. But for those that don't have familiarity, hopefully this is a teaser. Hopefully you stick around, stay interested in the presentation. I'm going to flash this slide again at the end, and hopefully, you can, in 5 seconds, take away those key points without any issue. All right, so now to start the sort of Roofline 101 course. What exactly is a roofline? So it's simply a 2D plot. Because we're good data scientists, we're going to label our axis. On the y-axis, we have our attainable floating point operations per second. And just the level set here. And I'm going to keep driving this point throughout the presentation. When I'm talking about flops and performance, it's always empirically measured performance, what you see on your specific device. We're not talking marketing numbers. We're not talking what you'll look up in a white paper. We're not talking about theoretical peaks, multiplying peak clocks times, instructions per clock. None of that. We're talking about what you are achieving on your specific device. And again, just to level set, a flop is a floating point operation. Some common operations for an add, we label it as one flop. A multiply is also one flop. And then an FMA, a fuse multiply add, we're actually doing two flops in that one instruction. Now, on the x-axis, we have this notion of arithmetic intensity. And I'm going to be calling it throughout this presentation AI. So not to confuse with your artificial intelligence, we're talking about arithmetic intensity. And this is simply a specific characteristic of your workload. And it indicates how much compute is performed per unit of data movement. And so I have an example here, a simple add operation. In yellow, we have our addition. So that's one floating point operation we're performing here. But in order to do that one add, we have to move some data. It requires us to do one read in green here out to global HBM memory for our Y value. And then it requires a write back out to global memory to our HBM for that orange X. And so if we're doing single precision here, FP32, each one of those is a 4-byte data movement. So 8 total bytes, and our arithmetic intensity ends up at 1/8. So hopefully that's clear. We'll keep going. And I don't have the chat pulled up, so if there are questions, please let me know. We can make this interactive. Okay, and so now, just to note, just to keep in mind here, empirical rooflines, these plots are typically done in a log-log plot. And, there's a lot of debate on whether it should be linear or log, but just, the common accepted way of doing it is a log-log plot. So when we look at these results, keep that in mind. Now we can get into these limiters. So in green on our roofline plot, we're going to have the peak compute flops for your specific device that you're running on, that you're testing. And then in red, we have our memory bandwidth, which is our arithmetic intensity times our peak bandwidth, global gigabytes per second. And again, these are empirically measured values. Whichever device you're running on specifically, whichever node, these results are going to be specific to that hardware, nothing theoretical here. Different SKUs, if you're doing on an MI210 or versus an MI250, 250X, you're going to have different results. Even if you're on the same, 250X on different nodes, if we get into the fine details of things, they might be slightly different because of yields and, voltage frequency curves. One might be able to achieve a slightly higher clock rate. So you're looking, what you get from a roofline plot is, what's your max achievable on your hardware. They're not theoretical values, nothing under any, unicorn conditions that we have on the slide. And I'm going to get into OmniPerf later and showing you how we get these empirically driven values, the test suite that we have. Okay, so now our attainable flops, what we can achieve on this hardware, is bounded by our peak flops and our bandwidth bound here, our red line and our green line. And then this interesting point, sort of in the knee in this roofline plot, is our machine balance. And the typical machine balance, so if you're on the machine balance, you're essentially leveraging all of the compute available in your hardware and all the memory bandwidth. So it's just sort of the most stressful point on your hardware, right? You're saturating everything the device can give you. There's nothing better you can do for your application if you want to, saturate bandwidth and flops, if that's your goal. And so your typical machine balance is usually around 5 to 10 flops per byte. And if you're working in double precision, that translates to about 40 to 80 flops per double you need to do in order to land a data point right on that knee to exploit the full compute capability. For MI250X, it's a beefy throughput device. We're looking at 16 flops per byte. So again, going back to our double precision, you need to be doing 128 flops per double of data movement to exploit the full compute capability, to have a workload that is compute bound on the MI250X. I'll pause there to make sure that's set in. And we're going to go through some examples to show how we can move along that plot, along that roof line. Now we can start to break up our roofline plot into specific regions of interest. Specifically above our green peak flops, that's unobtainable compute performance. You shouldn't be able to achieve a result that lands above that line. To get a result above that line, you would need to somehow improve your hardware. You would have to have faster clocks, maybe more compute units, something along that lines. But we shouldn't be able to set a point above that line. Similar with the bandwidth bound. You shouldn't be able to fit a point above that bandwidth bound. Again, you'd have to make some hardware changes to get a point over there, like increasing your memory clocks, or maybe adding some more memory controllers, maybe increasing to the latest and greatest HBM. Now, if you fall, typically, and then it's up for debate, I think the accepted is within maybe 50% of your peak flops. Again, keep in mind this is a log-log plot. You're considered to be compute bound. Your application, your workload is considered to be compute bound. And in this region, you're sort of reaching the diminishing returns. You put in a lot of effort, you might not get much performance. There's not much left to be had. And then we can do the same for the bandwidth bound. If you're within 50% roughly of your peak bandwidth, then, again, not much effort not much more performance you can achieve given the effort you put in. Of course, that leaves us with the area of interest. If you fall below those bounds, you're in the poor performance region where there should be some changes you can make to your application to better utilize the hardware you have available. And that's where you want to, as an application domain scientist, this is where you want to spend your time optimizing your workloads. And I'll get into some examples of how you can do that. So the final result here is, a simple singular plot where, we can present the architecture's peak achievable performance, empirically derived, but then you have this application and architecture agnostic view of how well you're performing, how well your application is leveraging the hardware available. So I like to drive the points home with examples. Let's say here we have a number of kernels in our application and we're running them on this new architecture. We want to figure out, how well are we doing? What should we focus our time on? Our manager or boss wants to know what kernels you're going to be spending your time on to improve overall performance, to get us more science throughput. Well, the first thing we do is we sort those kernels by arithmetic intensity. All right, let me go back here. So if you just have these, if you do the typical approach, just compute flops or some other performance metric, and you visualize it, and you look at this, you obviously think, maybe kernel F, kernel B, and kernel G are green, red, and purple kernels here. Those are the ones we should spend our time on. Those are the ones that aren't doing well on this hardware. We should spend our time optimizing those kernels. That's where we're going to get the best speedups, right? But if we go with our Roofline approach, first we sort our kernels by arithmetic intensity. And then we can fit them on this Roofline plot for our architecture of interest. And you can clearly see, going back one slide, our green bar there, which we originally thought was the one we should spend all of our time optimizing. When we put on this Roofline plot, we're actually sitting, almost on top of our memory bandwidth bound. So for this given workload, this arithmetic intensity, this number of flops per byte that we're computing, we can't really do any better on this hardware. We're limited by the bandwidth. If we wanted to improve performance, we're looking at things like, changing our algorithm, some pretty drastic changes in order to move it to a higher arithmetic intensity. And so if we keep going, it was actually these two kernels on the right, which one of them I think we had in our early guesses, but the other one wasn't the guess that we had. Those are the two kernels that we want to focus on. These two here, red data points. These ones have a high arithmetic intensity, but they're sitting pretty far off of our compute bound. So there should be some pretty low-hanging fruit changes that we can make there to improve the performance and get it closer to saturating our peak expected performance on this device. So again, so if you have a data point here, just to mention, you're kind of bound by HBM bandwidth, but there are some things you can do to shift it along this Roofline plot. Things like changing your algorithm, increasing your arithmetic intensity. Maybe you have a lot of data reuse, and so instead of reaching all the way out to HBM, maybe you can pull some data into your shared memory, which has a faster bandwidth. And so you're removing some of the data loads from HBM, so this should shift along the bandwidth bound. And I have this last note here. Kernels not near the Roofline should have optimizations that can be made. And this should is in this sort of chiller font, just because as we'll get into later with the examples, the Roofline plot isn't comprehensive. we're only considering flops and bandwidth on our device. But as we know, those aren't the only two sort of capabilities of our hardware. There's also things like atomics. There's things like latencies. There's things like transcendental functions, which don't perform at the same rate as your typical just FP32, FP64, your adds, multiplies. So some of those might be what we're limited by bandwidth or bounded by. Those aren't taken into account in this Roofline plot. So Roofline plot is sort of your introductory, you got something running on the hardware. How am I doing in terms of compute and bandwidth? All right, so now we're going to take a little sidestep here. Now that we've done the Roofline, we're all Roofline experts. We're going to look at AMD's profiler story, just to clarify things. And I'm going to tell you which one we're going to use in this Roofline tutorial. So the first tool that you have hopefully heard of is called ROCprofiler. And ROCprofiler is really the low-level API. I mean, it's as close to the hardware as you get. You're getting the raw collection of GPU counters and traces. And so when you're working with ROCprof, and I have an example, it requires a lot of effort sort of from the developer to provide input files, to parse the output files. It's usually in a CSV. But ROCprof will generate, also trace collection in addition to counters for the different levels on the GPU. And then you can visualize it with Perfetto. And then there's OmniTrace, which isn't discussed here. OmniTrace focuses on the tracing. Not only does it do the HSA, HIP, GPU, which it pulls from ROCprof, but it also pulls in some other things that it can put into your timeline, like OpenMP, MPI, Cocos, pthreads, a bit more information to fill in some of those gaps that you'll see if you just use a ROCprof timeline trace. And then finally, there's OmniPerf. And OmniPerf is what we're going to be focusing on in this presentation. And again, OmniPerf and OmniTrace and ROCprofiler, they're all public. OmniPerf focuses on the counters, and it provides you, your GPU speed of light, your memory chart analysis, and what we're going to look at here specifically, your Roofline analysis. It'll generate that Roofline plot for your hardware, and then it'll give you the data points for your workloads to fit on that plot as well. And again, so just to drive the point home with another example, say you're an application developer, domain scientist, you have three typical questions you're asking. You're usually asking, how well am I using the GPU? In which case, you'll look at the Roofline plot, and in which case you'll need to use OmniPerf. There's other use cases where, why am I seeing the specific performance that I'm achieving? And, you want to look at hardware counters. And again, you're looking at OmniPerf. It collects all those counters and presents them in a pretty straightforward way for you to understand. And then the last one is, where should I focus my time? Where should I be investing my effort to improve performance? And usually you'll want to look at a timeline trace so you can see where your hotspots are, where your runtime is being spent. And for that, you're going to use OmniTrace. But again, in this talk, we're just doing Roofline, which leverages OmniPerf. So I'll pause here for questions while I sip some water. No questions, let's keep going. Okay, so in all of its glory, here we have an empirical Roofline plot, hierarchical Roofline plot on MI200. I believe this is MI250X, so what's in Lumi. And it's hierarchical because we don't just have HBM. This is our HBM bandwidth bound, which I showed earlier in the Roofline 101. But we also have the rest of our memory hierarchy. We have our L2 cache, we have our L1 cache, and then we have our LDS or shared memory. And then on the compute side, we don't just have one compute bound. We have our compute bound if you're doing vector operations. And then we have your compute bound if you're doing matrix, your MFMA operations. Obviously, if you're doing MFMAs, you get a higher compute throughput. And then you have your data points for your workloads. And each one of these data points is going to be with respect, arithmetic intensity is going to be with respect to a given memory, location in memory. So whether you're looking at L2 whether you're looking at HBM or your L1. So hopefully that's clear. That's sort of our foundation that we're going to be using when we go through some of these examples. So on this slide, if we go to the bottom here, we have within OmniPerf, it's just a simple suite of synthetic kernels. You know, we're just having add kernel, FMA kernel, you know, an AXP, matrix multiplication, some pointer chasing, bandwidth kernels. We're just sweeping over all of those kernels and storing the results. And, you know, that's how we tease out our peak bandwidths for each of the cache for the HBM, our entire memory hierarchy, as well as the peak compute for vector operations, as well as the matrix. We're just sweeping over a suite of simple synthetic kernels. So I'll get through some examples in a bit later, but we essentially know, you know, how many operations we're doing per thread, you know, how many times we're looping over that. And so we have the total number of operations we're performing in a specific kernel. And then we're just measuring the runtime with ROCprof. And you know, obviously you have your total operations. If you're doing single precision, you have your total floating point operations, and you divide by your runtime and you get your flops per second. And something similar for bandwidth as well. We know how many bytes we're moving in these simple synthetic workloads. Yeah, you'll run OmniPerf, and again, I'll show that. Use just one command on the command line, and it goes off and runs all these synthetic kernels. It generates that plot. You send it over to the database so you can visualize it in the Grafana front end, and it will generate that plot. It'll look just like this, right? It'll have these plots with all the bounds, and then it'll have some data points for the workload that you ran. And you know, this could be a full application, all the kernels within that application, simple synthetic tests, you know, whatever you put through OmniPerf. It's all really automated for you. Yeah, so I guess I discussed that one. So here I'm simply listing all of the counters that we're using to compute these Roofline bounds, and you know, to generate one of those data points for your application to stick on the Roofline plot. And up here in the weight section, this is simply just for full disclosure, this is what we assign for each of these operations. Add, multiply are 1 flop, FMA is 2 flops. And then transcendental, depending on which vendor or whoever you're talking to, some might assign something larger. I use larger than 1. We're just fitting, you know, all of our transcendental functions, we're counting them as simply 1 flop. Yes, and then obviously a flop counts. We have different transcendental functions as well. And then when you're running OmniPerf, it's important to note that we can't collect all of these counters in one pass through your workload or your application. So behind the scenes, OmniPerf is actually running your application, your workload 3 times and collecting a different set of counters each time. And then here, after you've collected all those counters, these are sort of the equations that you need to compute to arrive at those different metrics, whether it's, you know, LDS bandwidth, HBM bandwidth, your compute flops, etc. So, I mean, specifically looking at the total flops calculation, we have all of the instructions for FP16, FP32, FP64. We have our adds, multiplies, transcendental functions, FMAs, and then you have all the instructions for your MFMAs, FP16, FP32, 64. So those are the equations after you've collected all those counters that you can compute if you want to do this all manually. Whereas OmniPerf does all this for you. You don't have to worry about any of this if you're doing OmniPerf. But again, just to be explicit and clear, you can collect all this yourself with ROCprof. This is how you would do it with ROCprof. First, you would just create this input file, this text file, and each one of these PMC lines, hopefully you can see it's not too small. Each one of these PMC lines is a different pass through your application that ROCprof will need to take, and it'll collect these specific counters. So if you want to do it manually, it'll take you 1, 2, 3, 4, 5 runs through ROCprof. Whereas OmniPerf, it's optimized. It can collect everything you need in 3 passes. Once you have that input file, you're just going to pass it to ROCprof. You're going to do ROCprof, pass in your input file, turn your timestamps on so you have runtime timestamps for all your kernels, and then the executable for your application. and ROCprof will do all the collection for you. The output will be this results.csv file. So again, you have to manually go through that CSV file, parse all the data, perform all those equations to get the final results. But I don't recommend any of that. That's just to show you the baseline if you want to get your hands dirty. Essentially what OmniPerf is doing behind the scenes for you. What I recommend is using, obviously, OmniPerf. And OmniPerf is a new tool released, I think, 2 weeks ago. It's open source. It's on GitHub. The goal is to, treat it as a truly open source project. We have our developer tracking that repo, so you submit issues, pull requests. Hopefully that's the way we can move forward with this project. It is not part of the ROCm stack. So if you install ROCm on your system, you're going to get ROCprof. You will not get OmniPerf. OmniPerf has to be downloaded and installed from GitHub. And yes, so it's built on top of ROCprofiler, so that's where it gets all its information from, all of its data. And it presents quite a bit of information for you to analyze your performance on the hardware, memory chart analysis, speed of light, and it's all visualized in this Grafana-based front-end GUI. And then I'm going to jump through this pretty quickly, but it's in the slides, and I think everyone will have access to slides. So on your own time, if you want to, you can go through it. But here, we're just going through instructions for installing the client on the compute node that you're going to be collecting performance on. Downloading it from GitHub, installing dependencies, installing this database, and then actual the client itself. And then there's also a server piece as well where we send our results to, and where it does sort of all the chugging through your data to analyze and present it, and present you with this Grafana front end for taking a look at all the results. Okay, and here we have a very simple example showing how simple it is to run OmniPerf to collect all this data. In this first step, all these lines, we're just building our test code, our vector copy example. And then down here, that's our one-liner for collecting the profiling results using OmniPerf. It's just OmniPerf profile, it's in a name that you want to name the output. And then you're going to give it the actual executable to run your workload. So here it's /vector copy. I think this is just the size of the array and maybe our block size here. So it's that simple. And then OmniPerf will run off. It will profile your application, and then it will also generate a Roofline plot. It'll run those simple synthetic kernels to generate the bounds on your hardware, the compute and bandwidth bounds. And then the next step is to send all that data to your server. So it's an OmniPerf database import. You're going to give it the host name that you're sending it to, which server is housing which host is housing your front-end server database. Give it the user. This -t it's a team name. It's just a way of organizing all the data that will be on the server. You can sort of group your workloads into these teams. And then -w, you're going to provide the path to results that you collected. And that will send it all off to your database for you to visualize in the front-end visualization system. Okay, so we have a Roofline plot. At this point, we've generated our Roofline plot. We see where our application sits on this hardware. I'm just mentioning here that Roofline is sort of the introductory step. You're finding how well your application is utilizing the hardware given to you. And from there, you can move into the rest of OmniPerf, which has analysis for HBM performance, L1, L2, LDS, the rest of your memory hierarchy. It has metrics explaining how well you're utilizing the shader compute units, how many wavefronts you're dispatching, your wavefront utilization, occupancy, and some other kernel statistics as well. So Roofline is just sort of the introductory, telling you how well your kernel's doing. If you find that it's not in that optimized region, well, then that's a kernel of interest you want to spend some time optimizing. And so you can step through the rest of OmniPerf and its whole collection of data to see if you can find where you can actually optimize and achieve some better performance. And so I'm not going to spend too much time on these slides. I'm going to go through the other pieces of OmniPerf. But again, you'll have the slides. So they're mostly to show you an example of what you expect to see if you generate, if you run OmniPerf on your own, you generate some results, visualize them in this Grafana system. Your results should follow something similar to what I'm showing here. So there's a speed of light analysis. Let's see. Yeah, so here we're just showing instruction data flow, performance overview of the hardware. There's also L2 cache and HBM data access information. OmniPerf really collects the entire kitchen sink on the hardware and then presents it in some visual manner to show you how well you're saturating some of the peak numbers on this device. You can step into the L1 data cache. You can look at the LDS or your shared memory, transactions, bandwidth. And then you can step into the actual compute unit, look at things like wavefront life distribution, your instruction mix, which is just telling you of all the instructions, how many of them are being performed in your scalar ALU, your scalar memory operations, vector ALU, branch instructions, so on and so forth. What your distribution of operations is. Obviously here we're doing lots of MFMA, FE64, your compute pipeline, and your memory access latency. So OmniPerf, the first step is doing that roofline analysis, and then once you've found kernels of interest, you can set through the rest of the data in that front-end visualization to figure out where your performance is being left and where you can improve. Yes, and some more information on other OmniPerf settings. Okay, so now we can jump into the examples, back to our roofline. And specifically, we're looking at MI210. No, I take that back. That was a slide I need to update. This is MI250X. So I'm going to make it a bit simple here. We're only going to look at the HBM bandwidth bound. We're not going to consider the L1, L2, or shared memory. And similar for the compute, we're only going to look at the peak vector throughput. We're not going to look at the matrix bound, specifically because these workloads aren't making use of LDS or the cache hierarchy, and they're not using matrix instructions. So, excuse me, I'm just going to remove them for clarity. We don't have a lot going on. And so here we have an actual roofline plot for MI250X. This is it's also the Frontier GPU as well as the Lumi GPU. It's important to note that when you generate these plots, MI250X has 2 GCDs, but your plot is going to be for a single GCD. Just like when you're on a node, you might have 8 total GPUs presenting in ROCm SMI. Your node will see 8 individual GPUs, even though there's only 4 MI250Xs. So similar here, you're going to generate 1 plot per GCD. And this sort of methodology applies to all MI200 series GPUs. MI210 only has 1 GCD, so you'll get 1 plot per MI210. And then MI250 is the same as MI250X with 2 GCDs. Okay, so now we can step into our first example here. And it's a very simple add operation, similar to what we showed in the Roofline 101 portion of the presentation. We're doing a simple A plus B. Both of them are stored out in our global HBM, and we're storing the result back out to A in our global memory. So if we look at the code here on the right, each thread is essentially doing one of these add operations. And I don't go into the details on how I'm setting up the grid, but that's not really necessary. So each thread is doing essentially 1 vector add instruction, 1 flop. In order to do that flop, we have to do 2 reads. We have to read A from HBM and B from HBM, our global memory. And then we have to do a write out to A. So a total of 3 data movements. And then they're, assuming we're doing single precision here, 4 bytes, 1 flop, that gives us an arithmetic intensity of 1/12. And so as we showed earlier, we can go through OmniPerf. We have this workload, we compile it. We run it within OmniPerf. It will collect some data points and generate the roofline plot. And this is what we expect to see on, I don't know what that is. This is what we expect to see in that Grafana front end for OmniPerf. Our add, which had a 1/12 arithmetic intensity, sits about down here. And we're pretty close to that roofline bound. Not sitting on top of the bound. And so the first question you might ask is, we should be pretty bandwidth bound, right? It's just a simple add instruction. But there are other things we can look at, such as, I didn't touch the way we're setting up our grid, our block size and all that. You can sweep over the different block sizes, 128 up to 1024, which is the max supported on 250X. See how that affects performance. Maybe it allows us to issue more requests in flight, get us better saturation of our memory controller. Or, maybe we can disable our cache hierarchy because we know we're going to go straight out to HBM every time. And we can do our non-temporal loads, which essentially disables checking in cache and goes directly out to HBM. But again, we're pretty close to that bandwidth bound. So it's what we expect for an add. So add had a very low arithmetic intensity. Let's move on to multiply. So here we have our x, which this time is just a simple scalar. Hopefully it's sitting in registers. So there's no data load for here. It's already sitting in registers for free. But B is still sitting out in our global memory. We have to pull it in. So we have one read for B. And then we're going to store the result back out into the global memory into A. And again, we're only doing one flop instruction here. It's a multiply this time, but it's still only one flop. So our arithmetic intensity ends up being 1/8. So we've moved slightly to the right on our x-axis on our roofline plot. So again, we compile this workload, we run it through OmniPerf, and we get another data point, which sits on our roofline plot. And we've moved, as expected, to the right. We're now at 1/8 on our x-axis. And again, we're very close to our bandwidth bound. Then you can think sort of the same optimizations we considered for add should apply for multiply as well. So hopefully this is pretty clear. We're moving up the memory bandwidth bound on our roofline plot. We keep it going. Now we'll take a look at the triad. And triad here, we have two operations. We're doing an add and a multiply. So two flops. X is sitting in registers, so there's no load out to HBM. But we are reading A and B. So a total of 8 bytes for A and B. And then we're writing out to A, so another 4 bytes. And so arithmetic intensity, two flops, we end up with 1/6. So again, we're shifting to the right on the x-axis of our arithmetic intensity. So we run it through OmniPerf. We go to the front-end visualization system, and this is what we see. Again, as expected, we've shifted to the right on our x-axis, and we're still bounded by our HBM bandwidth. How quickly we can read out of our global memory. So things are looking good, as expected. If you have a workload which has similar arithmetic intensity as these three, you're going to be fundamentally bound by our memory bandwidth. You're not doing anywhere near the number of flops per load of data to get it onto the compute bound. So last sort of synthetic test we're doing, and again, these are all purely synthetic. They're not, real applications here. As simple as it gets, we're looking at an FMA. Again, we're doing two operations here. We're doing another add and a multiply, but this time X and Y are sitting in registers. So we get another value for free. We're only reading A from global memory, and we're storing the result back out into our local register. And so now, again, we're doing two instructions. Hopefully, if you dump the assembly, when you compile this code, you look at the ISA, hopefully you'll see a V_FMA. So we're doing both of these operations in the same instruction. We're only doing one read this time. So our arithmetic intensity shifts, by a decent amount to 1/2. So we're moving again further along the right on our x-axis. So we should be moving up our roofline plot. So again, we run it through OmniPerf, we visualize it, we get our new data point, our FMA, sitting right there at 1/2 arithmetic intensity. All right, so hopefully this is all clear so far. We slowly moved up our roofline plot. Now, we just want to see what it takes. Let's see if we can sit a data point on this compute bound. What is it going to take to get us a point up there on this hardware, on MI250X? So to do that, we go back to our FMA example, but this time we're inserting this loop. Again, this is completely contrived. This is as synthetic as it gets, not something you'll see in an application, just derived so we can fit a point on the compute bound of our roofline plot. But we're going to just loop over this operation, NFMA times, which is 1024. So now we have this multiplier, 1024 times our 1/2. So our arithmetic intensity is, very inflated up to 512. So we're shifting far down the right on our x-axis. We should be able to sit a data point on our compute bound. So we run it through OmniPerf, it measures the performance, and lo and behold, over here at 512, we have our data point sitting firmly on the compute bound for MI250X. So if you, for whatever reason, had some workload that was similar to that, you would expect this similar performance. But again, it's a contrived example just to show us how we can fit a point on the compute bound. So the next question you might be saying is, we have this big gap here. What does it take to get points right around that knee in the roofline plot? So we do the same exercise, still with FMA, but we can see if we do a loop of 20 instructions, we're just below the knee. 30 gets us pretty much right on that machine balance, and 60 puts us over. So again, it's sort of driving the point with an example, the point I made earlier that in order to really saturate the compute on these devices, you need to have a lot of operations being done per data movement. I'll pause there for a second before I move on to the proxy application. Drink some water. With no questions, I'm assuming there's none in the chat either. Guess we'll keep going. So the last test case we're going to examine here is a proxy application. And it's a proxy application for many different computational science codes, similar to cosmology, astrophysics, molecular dynamics, applications like HACK, LAMPS, and AMD GROMACS, and that's N-body. And specifically, we're looking at the direct particle-particle method. We are looping over all particles in our domain and computing their interaction. And so it's computationally intensive. It's n-squared algorithm. And we have on this public repo the source code, so you can grab it if you want to play with it. It's, again, the fundamental particle-particle method. We have a collection of n particles in our domain, and we have to compute all n-squared pairwise interactions. In this case, I updated it so it's FP64. I think the publicly available one is FP32. It's just a simple search and replace. And then what's sort of great about this implementation is it provides multiple different implementations with different potential optimization approaches. So in this presentation, I'm going to cover the original implementation, which you can think of as sort of what's taught in Numerical Computing 101. And then this blocking approach, where we are pulling in blocks of data from HPM into our LDS, and then operating on those blocks in shared memory. But then there's other implementations like a SOA conversion, and then unrolling, loop unrolling. So as you can see, things get a bit more complex looking at, and this is still just one step up to a simple proxy application where we can actually count these flops and data movements. Obviously, if you're looking at a full application with a full kernel, things might be a bit more complicated. That's why we're sticking with something a bit simple here. So I'm breaking up. On the right, we have our force evaluation and body force evaluation. And I'm breaking up for computing arithmetic intensity, breaking it up into two different pieces. We have our n² piece loop here, and I'm calling that the interaction ops. And then down here, have our order n operations, and I'm calling this the accumulation ops. So in the interaction ops section, we're doing 3 vector adds, 6 vector FMAs, 2 vector multiplies, and then in orange here, we have this inverse square root, which we're counting as 1 division and 1 square root. But if you compile it, you dump the assembly, hopefully you should see this v_RSQ instruction, which is sort of an approximation, a much faster approach than doing division and square root on the hardware. And then if we move on to the accumulation section, we're doing 3 vector FMAs, 3 reads and 3 writes. And I forgot to mention in the interaction ops, we're doing 3 reads. So moving on to the arithmetic intensity for the interaction or order n² portion. We're doing a large amount of compute, and it's dependent on n. So n is the number of particles in our domain. For large n, in the simulation, I think we get up into the millions, maybe tens of millions. You can imagine your interaction arithmetic intensity is going to be very high. It's actually going to be pretty similar, actually more than what we saw for the inflated 1024 FMA synthetic tests we considered earlier. And then similar for the accumulation section. For large counts of particles, you're going to have a large arithmetic intensity. And so, like we did for our synthetic workloads, we're going to run this through OmniPerf. It's going to compute the roofline plot. It's going to stick these data points for this kernel on that plot. And so this is what you'll see when you load up the front-end visualization for OmniPerf. And it's kind of faint. Hopefully you can see that. Our arithmetic intensity is very high for this large particle count. It's actually moving off to the right of our plot that we generated. Need to extend that. The first thing you might notice is, yes, we have this very high arithmetic intensity. So, logically, as we've seen in the past, there's a high expectation we should have it sitting on, our compute bound. But you can see we're quite a bit off. And I hinted at this earlier in the presentation, going through the Roofline slides, the introduction slides. Roofline isn't, a comprehensive tool. It doesn't discuss and consider all portions of the hardware. One of the things that it doesn't take into account are transcendental functions. And on the hardware, doing transcendental operations, your cosines, your inverse square roots, they're going to perform at a slower rate than just your regular adds, multiplies, FMAs. And so that's sort of what we're seeing here. We have our inverse square root sitting on our critical path in our order n² portion. And we can see we're getting that sort of pulling down from our achievable flops. So you look at this, you might think, oh, there's performance to be had. I should focus on this kernel and improvement. Well, there's one thing that we can't really improve, and that's the rate of transcendentals on the hardware. So one important thing to keep in mind. And that's something you can see if you go through, the rest of OmniPerf, you look at the analysis, you'll see that the instruction mix, you're going to see a high count of transcendentals, and you'll just have to, use your knowledge from before that transcendentals run a bit slower. So hopefully that's clear. Now we get to move on one step past our, entry-level n-body implementation, and we're leveraging this blocking approach where we're preloading a tile size worth of particles into our LDS. We have our shared memory here. And then we're just going to operate on the data in shared memory. So we're effectively, again, we're in our plots, we're only considering the HBM bandwidth. And so as we pull data into LDS and we're operating in LDS, that takes away memory operations to the HBM. And so when we look at the HBM plot, we expect there to be a higher arithmetic intensity because we have less data movement into HBM. Some of that data movement is actually now going into LDS instead. So logically, before we even show the plot, we expect the arithmetic intensity for the blocking implementation to increase, to shift along the x-axis to the right. And then correspondingly, hopefully a shift up as well as we achieve a bit better compute now that we're operating in LDS. And so we can move along and we can see our data point off on the right, our filled in data point. We've shifted to the right. Now more of our memory instructions are going into LDS and not HBM. So our HBM data point here has shifted to the right and we've got a bit better performance, a bit better achieved flops overall. Any questions? This is my last example. And so finally, as promised in the beginning, here I am showing the results for a number of different workloads. We have our synthetic ones we discussed earlier, our adds, multiplies, triads, FMA, our inflated FMAs. And then we have some proxy applications in yellow, like mini-hack, XS bench, some of the kernels in Kripke, and then some full applications as well, like Quicksilver. And so you can see some of these, are NBody and mini-hack, which is a proxy application similar to NBody. It's leveraging the NBody approach. They're fairly compute bound. Then you have these applications over here, which are memory bandwidth bound. These ones, I would say, they're as good as it gets on this hardware. The effort you invest isn't going to really translate to a significant speed up. So I guess the last thing I was going to mention here, so the kernels that we would want to focus on are these sort of 4 kernels here. CMD, which is in Hack, is it uses a tree approach on the GPU implementation. So we're computing center of mass to bisect our domain and sort of split up our particle domain into smaller pieces. And so this, where we're computing center of mass, obviously there's probably some atomics in there, some bandwidth, and mixing with the compute. And so this is a potential source of interest that we might want to optimize. But again, another thing that Roofline doesn't cover, kind of leaves you hanging with, is it doesn't give you a notion of runtime. We haven't spent any time on CMD here because it's a very, very small fraction of overall runtime. Whereas, your NBody portion, that kind of sits on the critical path. We're very dependent on that. So another thing to keep in mind, put a grain of salt to each one of these results depending on how much runtime they're consuming.
So Noah, we had a question in Hack that asking whether this would work for OpenMP, and I believe the answer is yes there. But then we also had a question about huge kernels. So what has been your experience with real applications with this tool?
Yeah, so with real applications with huge kernels, obviously you're not going to go through and do the line by line counting like I did. How many bytes you're moving, how many floating point operations, and that's sort of the beauty of this tool. You don't have to. It will do all that counting for you, and then it'll put that plot, put your data point for your workload on that plot, and then if you are one of these applications down here, you get to step into the real meat of OmniPerf, and that's stepping through the counters and seeing the performance of your compute units, your wavefronts. It can be a bit overwhelming. There's a lot of data that's presented. So it's been immensely helpful for us application people.
Okay, today this presentation will be given by Gina Sitaraman. I hope I got that right.
Yes.
This is a new presentation on Affinity that we have gathered from various sources and enhanced. And Gina's been working pretty hard on it. So appreciate all her hard work on it. So Gina, go ahead and take it away.
Thank you so much, Bob. Without your help, this wouldn't be possible. That is the first thing I want to say. Bob and I work on an application optimization team at AMD. We work on many applications, and one of the first ones that I started with was CP2K, and very quickly learned that Affinity was a very important component. It plays a part in optimizing CP2K. So it is something that I have been using for the past couple of years, and so I know the importance of it, and that is why this presentation has been fun to work on. I also want to acknowledge and thank all these people who have helped put this material together. Tom Papatheodore from ORNL, Oak Ridge National Lab, he has given us permission to use some of his examples programs. Marcus Wagner and Alfio Lazzaro from HPE, they have given me scripts that I can show you here, scripts that I use as well. George has been helping me because I couldn't access nodes at Lumi. George has been helping me get the outputs that I needed by running on some Lumi nodes. Bill Knoll and KJ, we call him, they have all contributed towards the material here. Thank you all. So today's agenda, we are going to take a quick look at what modern architectures look like and what is Affinity, why is it important, what are the various concepts surrounding Affinity, and how do we understand node topology, what are the different tools that we could use. So we will go through some of those tools. And then especially, we're going to focus a little bit more on Lumi nodes in this presentation, but at the same time, we may give you an introduction to some other examples or tools or techniques that we can use on other systems. Hopefully, this will serve as a good reference for you when you come back to it later. And at the end, we will go through some examples of how to set Affinity for different cases and how to verify if we got the binding correctly. So let's get into how modern architectures look like. Today, we've got systems with multiple resources. We've got probably many sockets, and each socket has CPUs with many cores, and then multiple GPUs. We have several memory controllers, network interface cards, and these peripherals are often connected to one socket or the other, so they're local to a socket. And by default, the operating system controls the scheduling of processes, but it is not designed for high-performance computing jobs. So what is happening when the operating system schedules processes? The processes may be preempted to give way to something that is higher priority. And when a process is rescheduled on a new core, some of the data that was cached for it has also been moved. And the OS doesn't know the concept of parallel processes and the fact that they're all somehow connected. So let's get into what a Lumi node looks like. This diagram I have borrowed from Oak Ridge National Lab's documentation of Frontier. So it's very similar. Lumi nodes are very similar to Frontier nodes. And what we see here at first is there is only one socket. And if you look at the core numbers here, it goes up to 63. So we have 64 CPU cores. And here we have 4 big rectangles. Those represent the 4 GPUs that are MI250X GPUs. And each GPU, in turn, consists of 2 graphics compute dies. Those are GCDs. And those GCDs are connected with high-speed Infinity Fabric links. We also see that each GCD is connected to a set of CPU cores, a set of 8 CPU cores via a high-speed fabric link. And you see that each one is connected to a different set of 8 cores. And we have 512 gigs of DRAM memory. And finally, we see that there are 4 network interface cards. So 4 NICs that connect a node to other nodes in the network. So given that, we saw in that diagram something called NUMA. But what does NUMA mean? So these days, multiprocessor systems have this concept of non-uniform memory access, where we divide all the resources that are available in the system into some form of logical groups. So a NUMA domain is what we call a grouping of cores, memory, and other peripherals, all of these different resources. So in a NUMA system, you have a CPU core attached to its own local memory, while being able to access memories attached to other CPU cores as well. So what does this help us with? Local memory accesses are faster, while accesses to memory nodes that are in other NUMA domains will be slower. They will have higher latency, and especially if you had multiple sockets in your system, those accesses will take even longer because the socket-to-socket interconnect is not as fast. So another advantage to having the NUMA system is with local accesses, memory contention from CPUs is reduced. So it's only the processes running on the CPU cores that belong to this NUMA domain will be accessing the memory module attached to this NUMA domain. So those are some of the things we see here. And here I want to point out that if you look at any given physical core, there are 2 hardware threads running that can run on this physical core. And we also see that 8 physical cores here share an L3 cache. Okay. And okay, so LUMI nodes can be configured in one of 2 different ways. One is called NPS1 and the other NPS4. So NPS1 means there is only one NUMA domain per socket. So all of the CPU cores belong to the same NUMA domain. So what that does is it gives us all memory channels, 8 memory channels to interleave across for all the memory accesses. And it gives more uniform bandwidth, but slightly higher latency. Let's take an example. If you're running only one MPI rank, you may benefit from a higher CPU memory bandwidth because you have all of the memory channels available for use in the NPS1 case. Whereas in the NPS4 case, we have 4 NUMA domains per socket, like we saw in the LUMI node example in the previous slide. So in each NUMA domain, there are 16 CPU cores and 2 memory controllers. And so memory accesses in a domain are interleaved across only 2 memory channels. There is a potential for higher memory bandwidth because there is reduced contention and lower latency. But we may be vulnerable to hotspots unless we have all the processes spread across all the NUMA domains and all of them do similar amount of work. Then it is a good case. Otherwise, it may not be so ideal, right? With NPS4, affinity is very important, and we're going to see what affinity is next. And just want to point out that LUMI nodes are currently configured with NPS4, and for many applications, this is a more ideal setting. And very importantly, it is not something that the users can change. It is the site that administers this setting. It is a boot time configuration. So we have to go with what the site has decided. Okay, so what is affinity? Affinity is a way for processes to indicate preference for hardware components. So what hardware components, what resources do we assign a given process? Processes can be pinned to resources typically belonging to the same NUMA domain. Why is that important? Because we want to improve cache reuse. We want to improve memory locality. We want to reduce the contention for resources. As we saw before, we want to lower the latency, and we also want to reduce variability from run to run. And where is affinity needed? What kind of applications? It is extremely important for CPU-bound applications. So, for example, those that run on CPU cores and their data is in CPU memory, this is really important. When running on GPUs, it is less critical, except if there is a bottleneck with the location of data and host memory. For example, if you are doing, we have to do memory copies from host to device. And so for that, it is critical. But if there is page migration or direct memory access, then setting affinity may become very important for you. Within a GPU, affinity is far less important. So for parallel processes, affinity is not just binding. It is a couple of other things. We're going to look at what is placement and order next. All of these together, binding, placement, and order together, define affinity. So process placement indicates where a process is placed, what resources it's going to use. The motivation for us is to maximize the available resources for a particular application or workload. So we want to use all the workloads. Let's take some examples, right? Sometimes maybe we want to use all the resources. Or processes may have multiple threads and require separate cores for each thread. In some cases, we may want to use only the physical cores, and we may want to not use the extra virtual thread that's running on that core. Or maybe we want to have enough memory per process. There's a lot of memory requirements, so we may have to skip some cores. We just want to have fewer processes. In some other cases, we may want to reserve some cores for system operations. Or MPI, it prefers gang scheduling, whereas the operating system doesn't know that these processes are connected. So, and the reason is that when a process is waiting to be scheduled by the operating system, it may cause all the other processes to wait at a synchronization barrier. So there are different cases why we may want to choose placement properly. Until the last decade, placement was not that important because we only had very few cores. We had uniform architectures. We didn't have to deal with GPUs. And we had either distributed or shared memory systems. And whatever the OS did was okay. But today, we have to think about placement because we want to avoid oversubscription of compute resources and unnecessary contention. We want to make sure that all the resources are used uniformly. We want to avoid suboptimal communication performance when processes communicating frequently are placed far apart. And we also want to prevent unnecessary migration of processes by the OS. And what is good for us is that the affinity controls in the operating system and MPI have greatly improved and changed. Okay, what is order? Order defines how the various processes of a parallel job are distributed across the sockets of the node. So again, it is very important for processes that are communicating with each other to be close together. If they are spread far apart, then there's going to be higher latency of transfers. So that is the main reason. We also want to load balance heavy workloads by scattering across compute resources and avoid contention. So typically, we will find that there are many ways of ordering processes, and these we just brought up two of them. By default, you'll find that the processes are distributed in a round-robin fashion across sockets. For example, if we had 8 MPI ranks and 2 sockets, rank 0 is scheduled on socket 0 and rank 1 on socket 1 and so on. And what this helps us with is it maximizes the available cache and evenly utilizes the resources of the node. When we have a packed or close ordering, consecutive MPI ranks are assigned to processes in the same socket until it is filled before scheduling a rank on another socket. So for the same 8 MPI rank case and 2 sockets, we will find that ranks 0 to 3 are scheduled on socket 0, while ranks 4 to 7 are scheduled on socket 1. And when do we want to pack? We want to pack in order to make better use of data locality. And it is better if the ranks that communicate the most are using a shared cache or memory in the same NUMA domain. So that's a quick introduction to what we have in systems today, what affinity is, involves placement, order, and binding, and why they are important. Now let's look at, okay, when you get on a system, how do I find out what I have on that system so that I can make the right placement and binding decisions? So there are some tools. So even on a LUMI type system, the configuration may be different. Maybe the NPS configuration has changed one day, or some physical cores may be reserved for system operations, or maybe virtual cores are not enabled. Any system can have, it's on any given day, things may be different. So let's have a look at some of the tools. There's one called LS-Topo from the HWLock package, with which we can visualize node architecture. LS-CPU can tell us the CPU information. NUMA control shows us what is the NUMA configuration and the CPU core affinity for each node. And ROCm SMI helps us with understanding the NUMA node and the CPU affinity for each GPU device. ROCm SMI is a tool that comes with the ROCm stack. Okay, LS-Topo. This is an LS-Topo image of a LUMI node. And as you can see, it's quite complex. I couldn't zoom in far enough to fit on the slide. But I want to point out just a couple of things. There's one package. There's only one box in this entire image. So that is one socket. It refers to one socket. And there are 4 NUMA domains in that socket. That's the first thing we see. Let's zoom in a bit further. We are looking at NUMA domain 1. And we see that, okay, there are 8 plus 8, that is 16 physical cores in this NUMA domain. 8 of them are sharing an L3 cache. Similarly, this set of 8 share an L3 cache. And on each physical core, we have 2 hardware threads running. In each NUMA domain, we have 2 GPU devices. In our case, in the MI250X case, these are 2 GCDs. And there is a NIC in each NUMA domain. Okay. What does LS-CPU tell us? The first thing I look at when I see the LS-CPU, this is a filtered list. It doesn't show everything that LS-CPU shows. But I want to point out some important things here. So I will go and look at, okay, how many sockets I have, how many cores per socket there are, how many threads are running in each physical core. And that tells me whether hyperthreading is enabled or not. And in total, that gives us how many cores we have available to use, how many hardware threads. It also tells us that there are 4 NUMA domains and that this set of cores are attached, or the affinity of CPU cores to each NUMA domain is also pointed out. The same information can also be obtained using NUMA control-h, and it's a more elaborate form. So in each NUMA domain, you have this set of cores and how much memory is allocated. And also the distances between each NUMA domain. So this is not it doesn't have any units. It's just a way for us to figure out that it is fastest if you are reading and writing to the memory nodes in the same NUMA domain. And here we see that there are hardware threads 0 through 15 and 64 through 79 that are associated with NUMA domain 0. Okay. With ROCm SMI show topo, we can see the NUMA affinity for each GPU device. So for example, here we have GPUs 4 and 5, or GCDs 4 and 5, that are associated with NUMA node 0. And NUMA node 0 here is associated with the CPU cores 0 through 15. Okay, so this association, this relationship is very important. When a process is using, let's say, GPU 4, we want that process to be running on one of these cores attached to GCD4. GPU and GCD I'm using interchangeably, but this is a GPU device, which is nothing but a GCD in this case. Okay, so when we look at Lumi nodes in particular, what are some of the things that will affect our placement decisions? On a Lumi node, we see the same picture again. We see that each GCD is connected to a set of 8 cores via a high-speed Infinity Fabric link. And memory bandwidth between 2 GCDs of the same MI250X GPU is the highest because we have 4 high-speed links. You'll notice that different pairs of GCDs have different number of links between them. So GCDs 4 and 2 only have 2 high-speed links. 5 and 7 are connected only with 1 link. That's important. NICs are directly connected to odd-numbered GCDs. There are 4 NICs in the system. And we also can run multiple processes on the same GCD. So AMD GPUs natively support running multiple processes on the same GPU device. So we want to choose rank order and placement carefully in order to optimize communication. Okay, so we have discussed this before. If you are running a process that is using GCD4, you may want to run it on one of these cores that are closest to this GCD. And in this case, we see that GCD0 is connected to cores 48 through 55. Why is that important? It's because you want to have the fastest bandwidth for your host to device and device to host transfers. And because of the different number of high-speed links between different pairs of GCDs, if there are pairs of ranks that communicate the most, then you may want to place them on 2 GCDs of the same GPU device. Now, one thing to note is that even though these bandwidths are all different, communication using device buffers is going to be at least as fast as communication using host buffers. At least as fast. So the connection is even the slowest connection here is going to be at least as fast as the connection to the CPU cores. On a Lumi node, we have 4 NICs, and so they are connected to different GCDs, odd-numbered GCDs, and so inter-node communication using GPU device buffers is expected to be faster. So we recommend that you use GPU-aware MPI for your code. If there is MPI communication, it is better if you keep the data that you have just computed on your GPU in the GPU memory and use the MPI calls with those buffers. HPE or Cray, they provide environment variables for mapping processes to the closest NIC, so that those things can be used. I do not have all the details, but it is very easy to find. And we can run multiple processes on the same GCD. If each process does not use all of the resources of the GPU very well, then packing multiple processes on the same GCD will improve utilization. And depending on the communication pattern, we can pack ranks that communicate a lot on the same device. Okay, so rank order is very important. And we also want to keep most communication inter-node and not intra-node. And I'm sorry, apologies. You want to keep most communication within the node instead of going out of the node. For each application, it is the application expert or the domain expert who's going to know what is the best placement. But there are some tools that HPE provides that we can use to detect the communication pattern between the various processes, the various MPI ranks, and generate a rank order that can be then supplied to Cray's MPitch. So that I find that very interesting. And there are Slurm binding options to help you with the ordering as well. So in order to check if we got the right affinity, there are various methods. A quick way is to use top or htop to visualize where those processes are running. If you're using OpenMPI, you can use the MPI run has an option called report bindings that you can use to see which core and in which socket your process has been bound to. And then there are a whole bunch of different programs that pretty much use the same concept. We are going to take a closer look at the first two that programmatically can verify whether you got the right core, whether you got the right device, GPU device, etc. And thanks to all these people who have given me permission to use these. And in this book chapter, this is a book that Bob Roby wrote. He has different programs for different cases. Just OpenMP programs. You have MPI and OpenMP hybrid programs, and you can use those as well. Okay, so now we are getting to our last section. We are going to look at some case studies. I'm going to take serial applications as one example and MPI applications as another. MPI applications that can have multiple threads as well as use GPU devices. For the MPI case, I'm going to try to show the Slurm binding options because that's what we need in Lumi. But for the other case, these are all not particularly for Lumi, but these are all important to know. Okay, so for the serial application case, some examples using NUMA control. NUMA control comes from libnuma dev Linux package, and it can be used to set affinity. So for example, there is an application .exe, and we want to say that we want to run it on either core 2 or core 3, and we want all the memory accesses to be local to NUMA domain 0. In the second example, we are providing a range of cores for this process to be scheduled on, and we also want to interleave memory accesses between NUMA domain 0 and 1. So this is just like a drop in the ocean. There are so many options that you can play with. Please refer to the documentation for NUMA control. And to check if you got the binding right, you can use htop or top. Okay, so OpenMP offers a very rich set of environment variables that we can use to set up Affinity. So two main ones are OMP places and OMP proc bind. So places, OMP places indicates what hardware resources we would like to use. For example, do you want affinity to cores or threads, that these are hardware threads, sockets, L1 caches, or NUMA domains? What is your big category? And then proc bind tells how OpenMP threads are bound to those resources. Okay, so here are some examples. Now we are saying that OMP places equals threads, which means give each process a single hardware thread. And here there are 4 processes for which we give a couple of different physical cores to run on. And then in this case, instead of giving a comma-separated list, you can give a range. You have the starting core and the ending core, or the starting thread and the ending thread with a stride of 2. That's OMP places. So we are telling the OS that you can schedule on any one of these places. And the OMP proc bind indicates how the different threads of a given process are bound. So there are 3 options. One is close. It binds threads close to the primary thread. And the other one is spread. Now, if you have multiple cores that we can schedule on, spread those threads evenly on the given places. And if we say primary, that means we are indicating that we want all the different threads of the process to run on the same hardware thread as the primary thread, on the same place, whatever that place it is that you've chosen. And then there are some environment variables that you can use to print and verify whether you got the binding right. And again, OpenMP specification has got pages and pages of information about this. That will be very useful reference for us. And another very easy method, if you have used the GNU OpenMP implementation, you can use GOMP CPU Affinity to set up the affinity for the process and its threads. And here is an example of that. Here we are saying that we want to schedule all 16 threads of this process on cores 0, 4, 8, 12, and so on. And we can use this GOMP CPU Affinity to set the affinity for MPI processes as well, but we just have to use a helper script to set up this affinity for each process individually before running the actual application. We are going to see, there's an example of this in the exercises that we will do. So when we have these hybrid programs that have MPI and OpenMP and using GPU devices, we can use several methods. There are options in OpenMPI and Slurm. MPitch does not have so many affinity control options, but we can build MPitch with Slurm integration, and that allows us to use the Slurm bindings for setting affinity. The options that we show here today may not work tomorrow. It is just so things change all the time. So the recommendation is please read the man pages. It is possible that things won't work, but it's okay. The man pages of the version that you are using are going to have the right information. Okay, so here's a simple example that's borrowed from Oak Ridge. This is a program that when we run, it's going to print out what MPI rank it is, what thread ran on which hardware thread, on which node. So to get the hardware thread information, this is the most important function. It's called sched get CPU. And all the others you must already be familiar with. And in this example, I'm just picking and choosing some parts of the code, but the full code you can obtain from this link. To get the number of devices, we can use hip get device count. To set a device and get its PCI bus ID, this is a unique identifier for each GCD or each GPU device. So hip device get PCI bus ID will give us that. And everything else is the same. And here it just prints a whole bunch of information. What rank, what thread, where it ran, which hardware thread it ran on. And then, two differentiation here. There is RT GPU ID that is printed. This is the hip runtime GPU ID that's obtained from hip get device. And also the GPU ID is the node level GPU ID obtained from the environment's variable setting of Rocker visible devices. Okay, we are going to use these two examples. So on Lumi nodes, to set GPU device visibility, we can do it using one of two variables, environment variables. One is called hip visible devices. It restricts GPU devices visible to the hip runtime, and Rocker visible devices restricts GPU devices visible to the Rocker runtime. So these are two different runtime layers. The hip runtime depends on the Rocker runtime. So Rocker runtime is below the hip runtime. So whatever Rocker visible devices is making available is what the hip layer can see. Okay, so a simple way of initializing Rocker visible devices, when we run an MPI program, for each process, we can use a helper script to set this environment variable based on the local rank of the given process. So for each process, its local rank will decide what device it's going to use. So here I'm running an example. I'm running 8 processes, each having just one thread on one node. But I'm using this helper script before running my application under srun. So this script is going to set, and let's look at, this is MPI rank 0. And it obtained hardware thread 1 and GPU ID 0. I have these in red because this is not the ideal one that we want. And another thing to notice here is that all the hardware threads from 1 through 8 have been picked for each process. So they're all packed close together by default. Okay, what's wrong here? We know that in LUMI, the core affinity to each GCD is slightly different. So GCD 0 is closer to cores 48 through 55. GCD 4 is closer to cores 0 through 7. So in order to get an optimal performance on LUMI, we want to pick the right core for a given GCD. So either we can set the cores that we want to run on with the script that was setting the device for us, or we can change the script, like here, to set a given order for GCDs. I want GCDs to be picked in a specific order, and then we can leave the cores that are picked to be the order they are, from 0 through how many ever maximum we have. But when you run the same program, what happens is that MPI 0, the rank 0, got hardware thread 1, fine, and GPU device 4, that is good. All of the GPU devices picked are correct for each rank, because we want one rank to run on different GCDs, and we want them to run on the GCDs in the order that we gave them. But then what we see here is that the hardware threads are again all grouped in one NUMA domain, and this is not what we want. We want each hardware thread to come from different NUMA domains for each process. So what we need in addition is an srun option that says, I want to use only these particular hardware threads for my processes. And I will use my special script to pick the GPU devices in order. Everything else remains the same. I think we had to add this n tasks per node option as well. So here we see that, okay, for all the ranks, for each rank, you'll see, let's see, rank 0 got a core from NUMA domain 0, and then core hardware thread 1. Rank 1 got hardware thread 8, rank 2 got 16, and so on. And the GCD device associated with each one of those processes is also correct, optimal. You'll notice that I did not specify 0 there, because currently in LUMI, we do not find core 0 when you run with srun. And that's because a slurm option is preventing user processes from using that core. They call it the low noise mode. And let's take a closer look at what low noise mode is in a moment. Before that, I just want to show another example where we have 8 ranks and 2 threads per rank. And everything else is the same, except now we also want to have consecutive hardware threads be scheduled for each thread of a process. So for that, we have to combine srun's options with OpenMP options. And then we get, for rank 0, you have 2 OpenMP threads, and each one got associated with a different hardware thread. And both of them are running on GCD 4. Rank 1, same thing, they got from the next NUMA domain and the next GCD. The only problem is this doesn't work on LUMI yet. Things are getting set up. It's not there yet. So I ran this on Crusher just to show you how it would work. On LUMI, I had to use a CPU mask. So there is a slurm binding option that you can provide for each process and its threads, what cores you want them to run on. And this mask looks alien, but we have a way to generate this mask. But let's see what happens. So we have rank 0. It has, here we have 4 threads per rank, and we are running 16 ranks. So we are going to oversubscribe the number of, we are going to have 2 processes run on the same GPU device, which is, in this case, ranks 0 and 1 are running on GCD 4. And for rank 0, for all the different threads, they're using cores 0, 1, 2, and 3. And rank 1 are using 4, 5, 6, and 7. So they're all packed close. All the threads of a given process are packed closely. And since these two ranks are using the same GCD, they're all running on the cores, 8 cores that are closest to this GCD. So with NPS4, you want something like this. You want to have processes and threads on all the cores in each NUMA domain. And depending on your application, you may be able to oversubscribe the GPU. So this is the script that I used to generate the mask that I used previously. It was provided by Marcus Wagner at HPE. It has been super helpful. All we have to do is set up the number of ranks, number of threads, and the different core mapping that we want for each rank, and then it spits out the hex mask. Let's look at this low noise mode. When I zoom in to NUMA domain 0, I find that the first set only has 7 cores, physical cores. Core 0 is gone. So this is what LS-Topo sees, and we ran LS-Topo via Slurm. So it is a Slurm setting that is preventing core 0. The OS sees all the cores. Core 0 hasn't gone anywhere. It has just been reserved for system operations. That is done in order to reduce jitter and variability from run to run, and usually used for timing purposes. But this is what you see in the LS-Topo. We want to show this to you so that you are not confused when you come to it later. And so in that case, and some other special cases, right, you may want to reserve some set of CPU cores for system activity. In that case, again, just using a mask that is set up appropriately, only picking the cores that you want, is a good way to set up Affinity for your process and their processes and their threads. So in this srun command, there is also another option, which is the core spec, I think. It's basically you're saying reserve 8 cores for system operations. And we are using this mask. And in this case, we are running 7 threads per process and 8 processes in each node. And that is what we see here for rank 0. We have 7 threads and they all got bound. They didn't get bound to core 48. It starts from 49. Oh. Skipping a core. If your application is bandwidth bound or GPU bound, and if it is not multi-threaded, it doesn't matter. But low noise mode may be inconvenient if you have a CPU compute bound application, and that will hurt performance. Losing a core may not be very good. So we have to see, currently Lumi is set up this way, but we have to see if it's going to continue to be this way. And here's an example of the same kind of script where we are skipping the first 2 cores in each set and using that mask. So that's the end of the quick introduction. So in summary, for parallel applications, Affinity is really important, and it involves placement, order, and binding. Why Affinity is important is because we want to achieve high memory bandwidth, low latency. We want to optimize communication between the processes, and we also want to avoid excessive thread migration. And we just saw how to accomplish this, how to set up Affinity for the processes and their threads. For that, we need to know the architecture, and we have seen some tools that can help us with that. And we need to know the performance limiters of the application and design the best strategy. We also need to know how the processes communicate with each other in order to do the placement and order of the MPI ranks properly. And we also saw how to control placement and how to verify the binding with a combination of various options. We saw Slurm options, we saw OpenMP options, and in the exercises we'll see some OpenMPI things as well. That's all I have, thanks to all of my references here.
Can we borrow 5 minutes to
Yeah,
run
if anyone
through
has
the
a question.
exercises. So here are the Affinity exercises. You want to go ahead and walk through those, Gina?
Yes. So basically, after you allocate a node on this cluster, you can run ls-topo. If you provide the out.svg option, it is going to give you an SVG file, and that is the picture we saw in the slides. And then you can run ls-cpu, NOMA control, ROCm SMI, show topo to look at what is there on your system. And this is something that I do very regularly before I set up Affinity for my run. And let's take an example. This is the first one. The code is there in the link provided. The steps basically walk you through how to compile, and then when you run, there are different ways to run. So, for example, in this case, we are running 4 MPI ranks, MPI run, and we are using OMP places and OMP proc bind to pack all the threads that belong to a process close together, since we have 2 threads per process. And we see that rank 0 got hardware threads 0 and 1, rank 1 got hardware threads 16 and 17, etc. We are spacing the cores. Then in the second example, what do we do here? Okay, we are just showing that adding the report bindings option gives you a nice report from MPI run about where the processes and their threads are bound. We don't have that output here. We would like you to try that. And in the third example, if you ran only 2 MPI ranks, the output is not as expected. So what happened there? So rank 0, both OpenMP threads got hardware thread 0. And for rank 1, both threads got hardware thread 1. They didn't go to different sockets. On this system, we had 2 sockets. And it took us about an hour and a light bulb moment when Bob remembered that MPI run's man page says something special when running with just 2 ranks or 1 rank. So it always only by default binds to core when we run 2 ranks. So for the 2 rank case, we still don't know how to set affinity properly. It works for 3, 4, 5, everything, more than 2. And then let's go to case 2. Here again, you will download this example application, and then there's a simpler makefile. The makefile that comes with that is tuned to Frontier, to Crusher and Frontier. So you can use this makefile and build it. And then in order to run this MPI program with multiple threads per rank, we need to use and also be able to set the affinity for the GPU device and the CPU cores. We need to use the helper script. And I have provided a helper script that I use. And at the end of the script, you'll see that all that it does is somehow figure out what GOMP CPU affinity to assign and what Rocker visible devices to assign for each process. So the way to run that script is inside MPI run, just before your application, you would run the helper script. This is going to set up the environment variables for each process in the MPI run. So let's say this example, 2 threads per rank and 8 ranks. And we just ran the script that way, and we see that the binding is correct. And I would like you to verify if something is wrong, please let us know. And in the second example, we are packing 2 ranks on each GCD device. So then again, that should also be correct. So the output is here. This is just showing some ranks, or maybe all the ranks. In this case, it's all the ranks. Yeah, the GPU devices and the cores that are associated with that process and its threads have to be in the same NUMA domain. That is something for you to go back and check. Please use the slides for reference. I know this is quite dense. But I hope this whole thing has been helpful.